see the moon. Okay, we are now recording. That was the moon, Jupiter, and Saturn. What was it you said, Friday?
Yes, sir. This past Friday, they made like a tight triangle.
Uh-huh.
Yes, sir.
And so right now they're probably not quite as pretty of a triangle, but it probably still forms somewhat of a triangle. If you can go out and see it, Jupiter's the brighter one, Saturn's fairly dim, and the moon is approaching a full moon. It's gibbous waxing, right?
Okay.
Yeah. Okay. All right. Well, I've given just about everybody a chance to come in. Oh, and by the way, for people, so I just started the recording, some of the questions earlier had been about some of the tests and labs. I got this class caught up with a lot of the grading uh, last night, actually. And for those that were on the weekly activities, I got those updated, but I haven't been to the um, grade book to put in those that are not on the weekly activities. And so I'll try to get that done, but it's probably going to be the weekend before I get to that because this has just been a horrendously busy week. So I'll try to get all that caught up this weekend. All right, let's get any other questions, issues, concerns. I thought I had this up a minute ago, and now I can't see it. If someone sent me a message recently, I see something on chat, Microsoft Teams. I don't know what that is. But I had your screen up, and now it's not. Okay, so I'm going back to this one and open it again. Okay, and open it this way. There we go. All right. Now, in my last class, no, my second class this morning, evidently something on my transmission side was really screwing up because they said I was working on a slide and talking about it, and they said, "Do you realize your slide is all green?" I said, "No, it isn't. It's perfectly clear to me." They said, and everyone in the class, were like close to 20 students in the class, they all said the slide was green. so, so I went to the whiteboard, and then came back in, and it was fine. So if something looks like it really screws up, let me know, because everything will look perfect from this end, and I'll find out it's not. Okay, nowhere close. So we should have 9 students here. Yep, got 9. Okay, should have more than that, but y'all, I'm glad y'all are here. So I'm going to minimize this listing and set up to go from current slide. All right, before we get started today, let's just review where we are, where we've been, where we're heading. Okay. Oh, and one of the earlier questions was something, and I don't even understand what the Blackboard Ultra Stream is. If y'all ever figured out what good that is, let me know, because I think Angelica and Angelita was asking me something about in the stream. I don't even know what that is, what it does, or anything else. I had to listen to a bunch of things a couple weekends ago, sales pitches, and someone was talking about using the stream. I never did figure out what they were using it for or how they used it, but they acted like it was, God's gift to the mankind. But I don't know. But
Would have definitely made your job easier had you used Blackboard Ultra. You would have been able to write on it and do all the little fancy stuff that you wanted to do on the PowerPoint and make it bigger. So it would have been more useful for you. But you're getting ready to go on out and be free from work. So
Okay, well, what are you talking about now? I'm using Blackboard Ultra.
Oh no, I'm talking about the Blackboard. Like when you use Screencast,
Right.
instead of using Screencast, you could have used Blackboard. Isn't it? I thought it was called Blackboard Ultra.
No, it's
What
collaborate.
is it? Oh yeah, Blackboard Collaboration. That's what I'm talking about.
Right.
Okay, my bad.
Okay, yeah, that's equivalent to Zoom. And I can really do anything in Zoom that I can do in Collaborate. In fact, many people have told me that they they like Zoom better. It's got more features and more things. But I understand Blackboard Collaborate has gotten better, and it sounds like it might be fairly easy to do. But I heard others say um, actually that it can get hacked pretty easily too. I don't think anyone at the college has had problems with that, but I've heard that it has been. But yeah, the Zooming, Blackboard Collaborate are equivalent, but I can do anything I think they can there. It may be a little easier there, but I don't have to send the announcements every day, I guess. I don't know. I don't know how that works. But like you say, I am on the way out, so I'm not going to learn a new set unless I absolutely have to. All right, but let's talk about how we're going. Well, but that was something I don't think had to do with Zoom. It may have, but it was something to do with because my screen looked perfect and theirs were all green. And then when I went to the whiteboard and came back, theirs were fine. I have no idea what was what was involved with that. It may have been Zoom, I don't know. But anyway, here's where we are. We're in, we finished chapter 23 last time, except for the lab and the test. So what we're going to do today is start 24 and get as far as we can in 24 at 3:45, right? Yeah, we stop and we'll have the lab for chapter 23. Once we finish that lab for 23, then I'll post the chapter 23 test out there. And that way y'all can be working on your 23 test. Then on Thursday, like we've been doing the last couple of Thursdays, we'll wrap up chapter 24. And then, and we do have class all week next week, right? Tuesday and Thursday. Is that your understanding? Yay or nay?
Yes, sir.
Okay, that's what I thought. So that means then the next Tuesday, 1 week from today, we'll be doing, if we haven't finished 24, I think we will have, but if we haven't, we'll do the lab for we'll finish 24, then do the lab for 24, and then I'll post the test for 24, and then post the final for the course. So basically, we're going to be basically wrapping up everything next Tuesday, 1 week from today. You have until Thursday to turn everything in. I pretty sure I'll still be able to take it on Friday and even during the weekend. But I think grades will have to be in by noon on the following Monday. So if I don't have everything in by the beginning of work on Monday morning, I may not be able to get your grades in because I'll have full-term classes I'm teaching on Monday, so I won't have time to stop and put anything in. So basically, and that's why I'm trying to go on and get things over with so y'all have plenty of time to get everything wrapped up and turned in. Okay? So, word to the wise, kind of wrap it up. Okay? Any questions on how we're going to end this thing? Okay. Chapter 24, the last chapter, if you remember the course description, it said oceanography was one of the topics. Well, we don't have a full-fledged oceanography chapter, but basically this is doing it. Earth's waters. Okay? The picture here on the slide is a beautiful, I can't tell if it's a sunrise or a sunset. It's sort of hard to tell. It kind of looks more like a sunset to me, but it doesn't have to be. setting over the ocean, and you see what a perfectly level horizon that is. In your book, it's right down on the water, and whether it's coming up or going down, I think it's probably setting, but I don't know for sure. But the caption in your book says vast oceans cover more than 70% of the surface of the earth. Fresh water is generally abundant on the land because its supply is replenished from ocean waters through the hydrologic cycle. We're going to start with that. Now that's the same hydrologic cycle we started chapter 23 with. Weather and climate depends on the same thing. They all depend on the oceans. So that's where we're starting. The core concept here is this hydrologic cycle. The hydrologic cycle is, and we'll just start it, it's a cycle, so it goes around in circles. So we'll start in one place. Water evaporating off the ocean into the air, transport by the air masses, precipitation. Now some of the precipitation falls on the water. 70% of the surface is water. Some of that precipitation falls right back into the ocean. But much of it, or a good portion, falls on the land. Okay? And we know that once it falls on the land, it starts moving back to the ocean. Why? Because everything goes downhill. Gravity is pulling it downward. And when it falls on the land, even as it's in the highest mountains, even as snow falling up there, ultimately that snow is going to melt, and as it melts, it goes downhill, downhill, until it reaches the ocean again. So that's the hydrologic cycle. It starts in the ocean, it ends in the ocean. It may take a lot of shortcuts in between. Here's Diana. Well, she was already here, so she's coming back in. That still gives us, I guess, 10 students. No. Let's see how many we got. Yeah, 9 students plus me. 3, 6, 9. Got it. So, now, I wish this book and this slide set had a figure that I've seen somewhere, and I just don't know where it was that I saw it. And it showed a breakdown of water, okay? Earth water, okay? And it was really enlightening. I think it was something like a 55-gallon drum represented the ocean's waters, okay? And then a fairly small bucket represented glacial waters, okay? And then just an incredibly small amount, I can't remember what it was, a measuring cup or something like that, showed the other fresh water. I mean, it was just amazing at how much water we have, but how much of it is completely outside of our use currently, okay? And currently is a word there. Okay, never mind. We'll get into ocean currents later. So let's move on. I can't advance until I click on the slide. Okay, so we're beginning 24.1, water on the earth. Okay. Water is, and you may not think of it as this, but it's a chemical. Okay. If you think about it being a chemical, remember in chemical weathering of, oh, here's Brianna's coming in. That's good. Hold on a moment. Let me get Brianna marked. Brianna's here. Okay. That should get us up to 10 students. We broke double digits finally. Okay. But water was actually involved with every bit of chemical weathering of earth materials, solid earth materials. Remember, there was oxidation. Actually, water is a catalyst for oxidation. Piece of metal gets wet, it's a lot more likely to rust than one that is not wet. Okay. acidification. Acids are dissolved in water, okay, and so it's involved there too. Um, and then certainly solution, dissolution, hydration was the term that we used. It was there, okay. So water is a chemical. Of course, it's a pretty neutral chemical. It's a really balanced chemical. It's not a harmful chemical, but it's the most abundant chemical compound anywhere near the Earth's surface. Okay? Now, up in the air, you have a lot of other stuff, but guess what? There's more water mass-wise than there is atmosphere. We'll talk about that a little bit later. And we've already mentioned it covers actually a little bit more than 70% of the Earth's surface, covered in water. Now, 97% of that water is in the oceans. Now, what about the oceans? They're salty. That water is not drinkable. 97% of the water associated with the planet is in the oceans, salt water, saline, too salty to drink. Certainly great to sail over and do things with, but it's there in the ocean. Only 3% of that water is fresh water. Of that 3%, 2/3 of that fresh water is in the ice caps, or at least it was, okay? It's decreasing all the time. So about 2/3% in the ice caps, that's in glacial water, and less than 1/3 of the fresh water is actually available, okay? Now, when we say available, that means not in ice, but some of that is deep underground, okay? That's called groundwater. Others of it, and not very much, but some is in the air, in water vapor. Others might be in reservoirs and other places like that. But at least it's somewhat available. Now let's talk about that hydrologic cycle again. We've already mentioned it. Let's do the graphic here. If I could get the graphic to come up. Okay. Here. This is all the water on the earth is in that circle. Okay, let's just imagine that. And whereas here it said 97%, this says 97.6% is trapped and is in the ocean. That salty water, non-potable. In other words, we can't drink it because it's too salty. Okay? Fresh water is only about 2.4%. This says 3%. They were being generous here. Only about 2.4% is fresh water. Now, if you take this fresh water and draw its whole circle here, and this said 2/3 in ice cap, this says more than 3/4 tied up in ice, locked up in ice. So I don't know why the discrepancy here between their graphics and their text, but it is. This shows even more of that tied up in ice. Well, okay. Then, underground, in sediments, there's almost 80% here, a little bit more than 20% here, okay? That leaves just, and I wish that thing would move out of the way, in our rivers, streams, lakes, and so forth, and I can't see the percent there, 0.8%, less than 1%. It's in all the rivers, all the streams, that includes the Mississippi, the Great Lakes, everything else, less than 1%, 0.8%. In the atmosphere, I mentioned there was some there, is very, very little. 0.01%. I mean, it's very, very small. Important, but small. Okay, so let's move on to the hydrologic cycle. And you saw this exact graphic in the last chapter. Water evaporates from the ocean. The sunlight hits the ocean covers over 70% of the surface of the earth. So water hits that, the sunlight hits that, adds energy to the water. It becomes a water vapor, moves up into the atmosphere. If enough of that water vapor coalesces together, it forms clouds. The clouds get blown. Some of it falls back on the ocean, but some of it makes it to land. It precipitates there, as we talked about last time, either in the form of moisture, water, rain, or it comes down as solid, ice or hail. Okay? We don't get much of the ice or hail here. Lots of liquid water coming down, precipitating to the land. Now let's look at some of these percents. They're not all talking about the same thing. So I'll try to do this. This is kind of hard to do. Water evaporating off the ocean accounts for 84% of that goes into the atmosphere. Water also evaporates from the land. I'm looking out my back window here, and I see trees out there. And what are the trees doing? And I see plenty of grass and weeds and other plants and stuff. All those things are taking water up out of the ground, and we've had enough rainfall that there's plenty in the ground now, taking water up out of the ground, and this is only in the surface part too, it doesn't go deep, sucking that water up, and it's expelling the water. We call that transpiration. Ourselves and all the other animal life out there, we take in water either through our foods or through our drinks or whatever. And when we breathe, if you were to hold a cold piece of glass, a mirror works really well, in front of your mouth as you're breathing, you'll see you get water vapor on it because we're expelling water. Okay? But even the soil out there that doesn't have any immediate roots sucking up the water, it's evaporating water. Okay? And if all that's sending water into the atmosphere, think about what the Mississippi River is doing. Think about what the Great Lakes are doing. Think about all that standing. Shoot, in Alabama we have Lake Martin, Lake Logan Martin, Smith Lake, Gunnersville Lake, lakes all over, Lay Lake, all over the place. We have these lakes. They're evaporating into the air, water as well. So the ocean, 84% of the water that makes it to the clouds comes from the ocean. 16% is evaporated from the land. That adds up to 100%. Okay? Now, of that falls, 77% of the precipitation, that's rain or snow or hail or sleet or whatever, that falls right back into the ocean. 84 comes out of the ocean, 84%, 77% comes back in. Okay? 23% falls over land. Okay? Now, this is the one that's really bizarre. The runoff from the land, 7% goes back into the ocean. Now, where is that coming from? 7% plus 77%, that adds up to 84%. So the return to the ocean, 77% from rainfall or snow or sleet, and 7% coming off the land, that accounts for the 84% leaving to evaporation. So that's where those numbers come from. You don't need to know them, but just know the ocean's the biggest supplier, the biggest receiver. It's what's governing everything. So oceanography, pretty important science. Okay? So the precipitation returns water to the ocean either directly through rainfall or indirectly after it's been on land for a while. Okay? The water is transported to other locations. I think we've hit that and beat it to death. All right, any question on the hydrologic cycle? Goes around, comes around. It just always is happening. Now let's look at that is most important to us, perhaps, the freshwater part. That's the small part. That's this little bitty part here 2.4% of all the water on the planet, fresh water. That's what we're going to hit first. Later we'll hit the ocean water, okay? But let's deal with fresh water. Where does fresh water come from? Like we've already said, precipitation. That can be rainfall, it can be snowfall, it could be sleet, it could be hail. Any water coming out of the sky is precipitation. Now, again, here are the fractions in the number. 2/3 of it returns to the atmosphere, okay? Of that, I'm sorry, precipitation is the basic freshwater source. That's where we get most of our fresh water from, is from that rainfall, snow melt, ice melt, all that kind of stuff. 2/3 of this goes right back to the atmosphere, okay? Goes right back up to the atmosphere. Not immediately, but in time it does. The remaining 1% basically runs off, flowing downhill. That's part of it. That goes back to the ocean ultimately. But part of it also is absorbed into the surface of the soil and goes deep enough to be what we call groundwater. Now that can also emerge somewhere else as runoff, some lower area, and it does, okay? So even this, certainly the runoff goes straight roundaboutly back to the ocean. Even the groundwater can emerge as runoff. All right. The runoff and the groundwater distribution depends on several things. Soil type, and we talked about this before too, back in the soils chapter. If your soil has large particle sizes, that could include gravel, okay? It could even include rocks and boulders and things, but usually gravel, or sand. If it includes either of those, then if there's big particle size, there are big pore sizes, okay? That means the water makes its way into the ground, okay? If, however, your soil type is very clayey, meaning very, very, very small particle sizes, then the pore sizes are also going to be incredibly small. Now, there still may be a lot of pores out there, but they are such small pores, it's really tough for the water to get through it, okay? And a lot of times it doesn't, it runs off, or it sits on top and gets evaporated, okay? So the soil type is a big difference. Also, now this seems bizarre, the distribution depends on the dryness. What? Well, here's something, and it's rather bizarre. You might think that the drier a soil is, the more likely it is to absorb water. That actually is not always the case. When a soil gets extremely dry, okay, then it becomes what they call hydrophobic. When water lands on it, it beads up, just like it would on wax, okay, or something like that, because the water, the soil chemistry of the surface chemistry of it gets so it's all the bonds are tied up with other things, and none of them are there to absorb water. So actually, a moist soil will absorb more moisture than a dry soil will. And that's why sometimes when they have huge rainfalls out in the desert or in a barren area in California or somewhere like that, or a place that has had recent wildfires, a lot of times most of that water runs off rather than soaking in, okay? It's amazing. If a soil is already damp, then already the water has attached to soil particles and it finds its way through the pores pretty easily. Now, on the other hand, if a soil is saturated, I was over in Georgia this weekend. I'd been talking with my brothers on the phone, earlier, my older brother told me that when Sally, do you remember Hurricane Sally, was in the Gulf of Mexico, I think hit somewhere around Louisiana or somewhere, Mississippi, I think it was, maybe even closer to Alabama, Mobile Bay. It came in and then hooked around and went east. We were expecting to get a lot of rain out of that. We got maybe a quarter of an inch. Okay. However, it was moving east and a little north, and it smack went over our farm in Georgia. And they got more than 5 inches of rainfall in one day there. I guarantee you that soil was saturated. So once that soil got saturated, the rest of it's going to run off. So if it's too dry, it may run off. If it's too wet, it may run off. What your ideal condition is for the soil to be just a little bit damp, and then it soaks up the moisture pretty well. Okay, beat that to death, didn't I? The second of these is the amount and type of vegetation. Okay, now amount, how much of the ground cover is covered with vegetation. How much of the soil surface is covered with vegetation. And the more you have covered, the more the rainfall is able to get in. Okay, now maybe not right at first. If you have a lot of vegetation there, it may run off the leaves, especially if they're large leaves and stuff. But generally, the more vegetation you have, the easier it is for that soil water to find its way to the soil. When it does find its way to the soil, then it's trapped better. The more vegetation you have, you cut down the transpiration, the evaporation of that water. So it's a good thing to have vegetation covering the soil. Now, if you don't have live vegetation, a great idea to have mulch. In our pathway that goes back to the alley, we have pine bark mulch or cypress mulch, some sort of mulch there on the way, so the soil isn't bare. In the place where we usually sit in the backyard, the ground thing, to keep it from being muddy and the dog from getting so dirty and stuff like that, we have it covered with, I think it's cypress mulch. Okay, so the more you can, in most of our gardening areas, you know, either flowers or whatever, we always try to put as much mulch. It's vegetation, it's dead vegetation, but it still helps. Now, the other thing, of course, is the steepness of the slope. When we were over in the farm, I noticed some areas that were steeper. You could just tell where that Sally had just washed even the vegetation was laying down because the water was running on it so thick, where it was steeper. Where it was flatter, then the water tended to accumulate, sit there longer, so it was able to seep into the soil better. Then the other thing was the rate of rainfall. Okay, if you have this rain coming down, hopefully, boy, wasn't it yesterday that was just about a drizzly rain, or maybe it was Sunday, a drizzly rain all day long. That's the best kind of rainfall for absorbing water into the soil. Very little of it runs out. Well, Denisha must have had to leave and come back because I already had her here, but she's coming back in now. Glad she made it back. Okay, so the rate of rainfall, if it's coming down too rapidly, the soil can't possibly absorb it all, it's going to run off. If, however, it's coming down very slowly and all your other conditions are ripe and you're not too steep, then much of that rainfall will make its way into the soil. I'm all in favor of as much of the rainfall making it into the soil as possible. I'll give you an example of why. Over in Georgia, my younger brother lives just south of where my part of the farm is, and he had a pretty good well there. Always had good water in it. My grandmother lived there before he did, and I used to stay with her when I was in high school, just to have someone in the house with her. My older brother and I swapped off on that until he went off to college, and then I stayed there most of the time, and it was good water. It was better than the water we had across the road at my parents' house. That sometimes could get sort of contaminated by mud and stuff like that, but her water was really good. Well, Dan was telling me that as the years went by, over in Georgia they had close to a decade of pretty severe drought. They only had like 2 years out of 10 that had decent rainfall, and the rest of the years were very, very dry. And some of the big farmers in the area put in deep, deep wells to irrigate their crops, okay? And they drew down, and we'll talk about this later, the water table. And my younger brother said that his uh, well water started tasting sulfury, and that this year, with the advent of all the rain that we've had this year, and for the last several years we've had good rainfall, that finally the water is tasting good again. Well, that's why I'm all in favor of as much water making its way through the soil as possible, and we'll talk about this later, in order to raise the water table. We'll talk about that later. So there's fresh water. I must have talked so long it won't advance. Let me click there. There it goes. And here's an illustration of this. Water comes from the sky, precipitates onto the land. Okay, in land that's highly dissected like this, then a lot of it's going to run off, downhill, pretty rapidly. Downhill, pretty rapidly. However, a good amount of it makes its way through the soil into what we call groundwater. That's what I was referring to earlier. And remember, we said this earlier, groundwater is, where was that slide? Yes, groundwater is the water that absorbs it. I thought it had a percentage here. I don't see it here. But that's the water that makes its way into the soil. Okay. However, and we did say this as well, that some of this groundwater also makes it into runoff, because up here the groundwater is going down, but then downhill here it actually goes back into the stream. Some of this is coming out of the stream, but some of it goes into the stream and winds up running off after all, even though it was originally groundwater. So even groundwater will make its way back to the ocean. We want it in the ground as long as possible to keep the water table up. Now, let's talk next about surface water. Again, this is the smaller part. Now, before we do, in your text, there is a great blurb, very good blurb, on water quality. I don't know if you can see that. Why can't I read it? Oh, there it is. It's on the other side. There it is. Water quality. Science and society. Water quality is the title of this blurb here. Really a good read. And it has some questions, okay? I think they call them questions to discuss. So you might want to find a paper topic there. Hint, hint. We have this week and next week, and that's all, folks. Okay. Today is the last class day we'll have in September. If you want that last bonus point, you need to get your papers in today or tomorrow. If they come in Thursday, you just get your score. If they come in today or tomorrow, you get 1 bonus point. Okay? So please, folks, don't forget about your research papers. The instructions are out there. Look under week 1, handouts. You'll see research paper instructions. And please don't forget about your research paper. I have had several of them turned in. I may not have posted all the grades on Blackboard on the grade book, but I have 1, 2, 3 in my grade book. They may not be on Blackboard yet. And there may be some more that have been turned in that I just haven't printed off of emails and stuff. So I'll try to get that done this weekend. All right. So there was Science and Society, water quality, a really good blurb to read. Now we're going to talk about surface water. Now that's collectively all the water in all the streams. I can't think streams in the city of Birmingham without thinking of Village Creek, because you always hear them talking about Village Creek. But all those creeks, all those streams, all the ponds, all the lakes, all the reservoirs, okay, naturally occurring lakes or reservoirs, which are man-made lakes, all that is what we call surface water. It's sitting on the surface of the soil. It's not soaked into the earth. That's your surface water. Now, here's a concept, an important one. That is a concept of a watershed. That's not a shed where you store water. That is where water is shed from going somewhere else. That's the land area drained by a stream or a series of streams. Now, we happen to be at kind of the base of Red Mountain is where we live, okay? And coming down from the south, that's where Red Mountain is, pretty steep hill coming down here. Coming from the east, there's a gradual hill coming down. Coming from the west, there's a fairly steep hill coming down that way too. And going to the north is just a really gradual stretch going to the north. Well, guess what? All the areas around this highland on three sides is all shedding their water down our street, either the one we live on or the one coming down the hill, and then it makes its way down the street that's on the side of our house, okay? And when it rains hard, that thing's a torrent. I can't keep soil over there. It washes everything away. It just goes, the drainage system, what they call the storm sewers, cannot accommodate all that water coming in. Okay, so that's what we sort of mean by a watershed. The land area drained by a stream or streams that rode to the immediate west of us, that becomes a flowing stream. It's not really a stream, but you know. Now, if you have two adjacent watersheds, okay, if you go on up Red Mountain and then down the other side into, say, Homewood, well, guess what? Part of the water comes our way to the north and part goes to the south into Homewood. That two adjacent watersheds are separated by a divide, and Red Mountain would be a divide. Shades Mountain would be a divide. Double Oak Mountain would be a divide. All those ridges, Shades, Shade Crest, that's what it's called. Shade Crest Drive basically goes along the crest of Shades Mountain. Well, guess what? It's a divide between that water that runs off basically to the north and that goes basically to the south. That's called a divide. Okay? Now, the entire country then, when you combine all the little watersheds together and all the divides together, you basically have what they call a continental divide that separates the watersheds that drain on opposite sides of the continent. And there is a great graphic, I think it's here. Yeah, here it is. Incredibly impressive graphic here. Okay? And I'll do my best to explain what's going on here. This huge area here is basically called the Mississippi River watershed. Now, it's not just the Mississippi. Here's the Mississippi, flows into the Gulf of Mexico down here in Louisiana, and it comes up here and forms a boundary between Mississippi and Louisiana, between Mississippi and Arkansas, between Tennessee and Arkansas, between Tennessee and Missouri, between Kentucky and Missouri, but okay, that's the Mississippi River, between Illinois and Missouri, between Illinois and Iowa. That's the Mississippi River. This is Minnesota up here, I think I have that right. No, this is Wisconsin here. This is Minnesota. The Mississippi River basically forms a lot of that boundary here. So this is the Mississippi, but you have the grand old Missouri River coming in that goes across the plains like this. You have the Ohio River coming in here. And I'm trying to remember where the Tennessee River goes. I think it goes straight into the Gulf, so it doesn't make its way to the Mississippi. But over here in Texas, I think this is the Red River here. There's just all these other rivers that feed into it. So the biggest watershed in the U.S. is the Mississippi River watershed. Okay. Now, what forms its boundaries? Well, pretty much what you see here is the Appalachian Mountains. Not completely, but going through West Virginia, part of Pennsylvania, Virginia, Kentucky, uh, Tennessee, a little bit of North Carolina here, and into the corner of Alabama. That's the Appalachian Mountains. That is a minor continental divide. That's called the Little Continental Divide. It divides the eastern part of the U.S. from the middle part. Okay? Pretty much everything to the east of this flows into the Atlantic. Okay, here's the Savannah River coming down here. There's the Mulgee, the Oconee, all the rivers here, a little river in south of North Carolina, the Petey River, all the rivers that flow into the oceans here, they're separated by the Appalachian Mountain Continental Divide, the Lesser Continental Divide. Now, some of the rivers down here, like Apalachicola, that came from the Chattahoochee River combining with the Flint River and some other rivers in Georgia, they flow into the Gulf. But the Mississippi is the biggest feeder in here. Now you have other rivers here that flow into the Gulf. The Rio Grande that forms a border between Mexico and Texas, that flows into the Gulf. So these are all watersheds too. Every one of these is a watershed. You know, somewhere over here, these are smaller watersheds. But this is the biggie. Huge area of the U.S. flows this way. Now up here, they flow into the Great Lakes. The rivers go into the Great Lakes, okay? These go into the Atlantic, but these largely go into the Mississippi. The Missouri, the Ohio, and all the other rivers into the Mississippi. Now, the next biggest watershed, and these two are almost the same size, I don't know which one's really bigger, Columbia River watershed. The Columbia River is the river that forms the boundary between Washington and Oregon, I think, or maybe it's just north of that border. But the Snake River runs into it, and the Snake River runs, I think, the border between Idaho and Montana. But anyway, all this is the Columbia River watershed. The Colorado River watershed flows into the Bay of California ultimately down here, and it goes this way. So that's another big watershed area. So those are the three biggest in the U.S. These are pretty good size. I'm sure the Rio Grande watershed area is a pretty substantial one, but they're all much smaller than these three big ones. So those are the three biggest, with the Mississippi River watershed being the very largest. Now, what is this line here? That's another continental divide. A divide separates two adjacent watersheds. This is the big continental divide in the Rocky Mountains, and the water on the east side of this flows into either the Gulf of Mexico, ultimately into the Atlantic. Everything to the west of that flows into the Pacific. Okay? So, that's what we mean by a divide. But every little watershed you have is separated by a divide from the next adjacent watershed. Okay? So, and the continental divide separates watersheds draining into opposite sides of a continent. To the west goes into the Pacific. To the east of this goes into the ultimately into the Atlantic. It may go by way of the Gulf of Mexico, but that's going to go into the Atlantic eventually. The Appalachian divide here separates that going, some of that going into the Gulf of Mexico and some of it going into the Atlantic Ocean. Most of it ultimately goes to the Atlantic Ocean, even though, but there are some other minor watersheds down here. I know in Florida there's the Peace River, up in Nebraska the Republican River right here. So there's other rivers around, but many of these feed into the bigger watersheds. And that's what a divide is. A continental divide is what separates a continent, what goes east and west. Now, a very interesting thing, when my wife and I were driving through Yellowstone, which sits in the northwest corner of Wyoming here, some of it into Montana. I don't know if any of it goes into Idaho or not. I don't think so. A little bit of it is in Montana. But anyway, when we were driving through there, they don't have this line exactly right, but we were just going back and forth over the Continental Divide because it sort of winds around, the roads wound around, and we were going, and as we were driving, there was almost always water flowing somewhere on one side or the other of us, and we'd look, it depends on which side of the Continental Divide we were on, we'd say, okay, that water is flowing north, that's going to the Pacific. Okay, it's water over here, we can't tell, it looks like it's flowing, yeah, but we had to see which side of the divide we were on, and that water is going this way, the other water is going that way. Right there in Yellowstone, Yellowstone has the Continental Divide going smack through the park. So on some sides you're going to the Atlantic, some sides you're going to the Pacific. Okay, it's pretty interesting to look at the rivers and watch them flow in opposite directions, knowing those two rivers are never, they're within less than a mile from each other. They'll never mix their waters at all because one's on one side of the divide, one's on the other. All right, after surface water, which is all the rivers, lakes, streams, reservoirs, and all that kind of stuff, we have groundwater. This is underground water saturating open pore spaces between rock and soil particles. It percolates downward through the surface. That's why I love to get that rainfall to make its way through the surface soil. 25 times larger supply than all the surface freshwater put together. All the rivers, all the lakes, all the streams, all the creeks, all the everything. You got 25 times as much stored under the soil. That's the groundwater. It's often within 100 meters of the surface, sometimes deeper. Now that's 300 feet. That's one football field down, okay? So it goes pretty deep, okay? At the farm in Georgia, when my dad, before we moved to the farm, and he was farming it, we lived 7 miles away in a little house up there in a next county, actually. But he would drive down to the farm, do the farming. But he had to drill a well on the farm so he could water the cattle and stuff like this. There was a water source, but it wasn't reliable. It could dry up, so he drilled a well so he could water the cattle there. And that water, oh, was fantastic water. And it was only between 100 and 125 feet down. Wonderful, wonderful water, okay? So it was only about a third of that 100 meters, okay? Then later when we moved down, we had to drill a well on that side of the road where the house was. It wasn't nearly as good a water. That always got muddy and stuff like that after a heavy rainfall. So it was not nearly as good a quality water as it was over at the cows got to drink. Well, then when my younger brother drilled his well, actually my grandmother drilled the well, or had it drilled, and it was pretty good water. It was not maybe quite as good as the shed, but better than across the road at my parents' house. And then ultimately my older brother drilled a well on the north end of the property. It was really sandy. The water tastes pretty good, but it did have sediment in it. But then when we drilled our well, when we built the 2-bedroom bungalow over there, they could not hit, they hit water somewhere around 150 feet, but it wasn't sustainable. They pump it overnight, and if it dries up, that means it's not sustainable. So they had to go deeper and deeper, and they actually went down 250 feet or so, something I don't remember exactly. So they were very close to this 100 meters here down. But boy, it came up really, really good water. A lot like the water at the shed had been. And that well ultimately dried up when all the farmers around, not close around, but started drawing down the water table, and the droughts and stuff like that were not replenishing it. They had to go deeper, and when they went deeper, even though it's just a few feet away from the previous one, wasn't nearly as good a water. Okay, but that's groundwater. It's down there. You just have to tap into it. Now, how does that groundwater flow? If it can find areas of sand and gravel, again, sand is large size soil particles, gravel is even larger, and when you have large size particles, you have large pores. When you have large pores, that's very permeable to water flow. That's the key. A clay, on the other hand, now this is where I have a little bit of problem with the way they word things here. Porosity is how much total pore space you have. Clays have in general, will have just as high porosity as, say, normal soils will. Maybe not quite as much as sand, but just pure sand. Certainly not as much as gravel, but they still have, for most soils, the porosity is the same. Sometimes clays actually have more pore space. The trouble with them is the space is so tiny. Okay, now that doesn't seem to make sense, but catch this. You have lots of tiny pores. Lots and lots and lots of tiny, tiny pores. But guess what? And this is the example I give. I may have given it to you already. Have you ever stopped by, say, McDonald's or a place like that in the morning to get that cup of coffee to get you going in the day, and they provide that little bitty, I call it a swizzle stick, that you can suck the coffee through and not burn your mouth so awfully badly, okay? That hot coffee will go through that tiny, tiny little tube. Well, if you happen to go back by in the afternoon and you're just really craving a milkshake, do you think they're going to give you that same tiny little straw, that swizzle stick, to suck your milkshake through? If they do, you'll pop your eardrums. You'll not be able to suck that milkshake through that tiny little tube, that little swizzle stick. Okay? Even if you had a bunch of those little swizzle sticks, it'd be so much better to have a big old straw. Now, it's not that big, but a straw. Why? Because it's not just the porosity, it's the pore size. That's what makes sand and gravel so permeable to water. The pore size is large. Clay has incredibly small pore sizes, but it may have as much porosity. You may have 300 times as many little pores, but they're so incredibly tiny. It's hard for the water to move through them. So sure enough, the impermeability happens when you have small pore sizes. Okay, here's Andares. Now, was he here before? I thought he was. Yes, he was. Okay, so he's coming back in. Now, it also happens that you can have low pore porosity, small pore volume. That's certainly going to be impermeable. Now, here's what happens. Just the fact that they say it's impermeable when saturated, okay, that means you may have plenty of pore spaces, but if they're filled with water, no new water can go through. And when you have clays, which have very tiny pore sizes, and they get saturated, it's really hard for that water to move. It'll move better through big pores than it will small pores. Okay? But the other thing that happens with clays can pack down on each other. Now remember your gravel and your sand, okay, and Darius is coming back again. You must have trouble getting in and out, so he's coming back. Okay, now the other thing about gravel and sand, you can run over it and press it down and it just moves on you, okay? And you really don't decrease the pore size any. But clays, if you run over them and pack them down, those really tiny pores you have, they get even tinier, and you get fewer of them because you pack the soil particles against each other. And they do form in plates, so it makes it even harder. The water has to run more horizontally than it does vertically. So those are the issues why a clay is more impermeable. It's not necessarily low porosity, it's small pore size, okay? Though you can have lower porosity when you compress the plates together and now there's no pores left. You have low porosity. So it certainly affects it, but generally in most reasonable clays that haven't been run over by equipment or vehicles and things like that, you have the same porosity, it's just very, very small size. And that's what makes it impermeable. Okay. I think this illustration, if I can get it to come up, will show that. Large particle sizes lead to large pore sizes, and water can go through pretty easily. Now, small particle sizes like clay particles, and these are even large for clay particles, if you were to add up all the pore space in here, you're probably not going to be too far off from the pore space in here. It's just that this is incredibly tiny pore space. Lots of it, but it's really tiny, and water has a hard time finding its way through. Let's say it's trying to come through here, and it hits a dead end, and then it goes here. Well, this is showing always a way out, but right here, it hits down here, there's no way out, okay? So it saturates above here and is dry below there. So that's the problem with clay particles. There's no way this is going to stop the flow of water because the pore sizes are so big, the water flows on through. Here it sits on top and runs off, okay? So that's the illustration. Not a great illustration, but a reasonable illustration. They did make the clay particles as if they're flat plates, and especially if they get run over, they get the same orientation, and that really makes it hard for water to find its way through. Okay. Now, remember they said back here, groundwater was underground water saturating the open spaces between rock and soil particles. Okay? Percolates downward from the surface, blah, blah. Okay. When it does percolate down, you'll run into areas where it actually saturates. Now, usually what happens then, the collected groundwater is above some type of impermeable layer. Now, it could be a clay layer that's somewhat impermeable. More likely, it's a layer of rock, often called the bedrock of the area, not the Flintstones town, okay? Okay, the impermeable layer could be actually stone, rock, okay? So the water table is that top boundary of that zone of saturation, okay? So the bedrock is down here, the water saturates everything on top of it, and then it's top of the water table, that's called the water table, the top boundary of the zone of saturation. Above that, you got some water, but some pore space, you got some air. Below that is all water, okay? That's called the water table. Now, when you have these large areas of water saturation like that, that's called an aquifer. And this is basically kind of like an underground river or stream or creek or something like that. That's what they mean by an aquifer. It's a subsurface layer of highly permeable materials, and this is sort of bizarre. It says highly permeable material capable of producing water. No, it's capable of transmitting water. Okay, it doesn't produce the water, it transmits the water. It allows the water to flow through. Now, if these are deep, deep, deep waters, they're called artesian aquifers. They are confined under pressure from water at a higher elevation. And this next graphic is fairly good, but it leaves a little bit to be desired. Okay. Down here you have your impermeable layer. The odds are it's probably bedrock. Okay. Granite, limestone, something else like this. Now the good news about limestone has a lot of cracks and pores in it, so even that's not a totally impermeable layer. Granite, though, is pretty much impermeable. Somewhere down there you're going to get an impermeable layer. Could even be a clay layer. Most of the time it's not. Okay. But then above that you have your soil particles. It could be sands, gravel, could be silts or loams, or maybe even clays that are saturated, but that is pretty permeable so the water can go through. Now, if that happens to cross the surface here, you get a natural lake here. This is saturated permeable layer, but it's level with the top here, so you actually get a lake. Or you get a river down here that's flowing through. Or you get a swampy area here. Anywhere that saturated layer breaks through the surface, you're going to get some sort of standing water. Okay? A swamp type area, a river area, or a lake area. Okay? Now, this is another illustration of what they were saying earlier. Some of this groundwater, this is all groundwater here. This is surface water. That surface water, that surface water. This is groundwater. Look at this. It goes out and leaks right into the ocean without breaking the surface. Now, yeah, some of this river water will come down to the ocean too, but this will actually leak in through the sides of the ocean, coming in that way. Okay. Now, if this were deep, 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 and I think the next slide is going to show that. Yes, if there is a area that receives moisture, now here's the, we don't know what this layer is here. Maybe permeable, may not. This is impermeable, that's impermeable. In between, you have a nice aquifer, an area that water can go through. Now, if that water is coming from a higher elevation, but this is very, very deep here, then you may have what you call an artesian well here. Now, that's what we thought, and we still think the original well at the farm that was such good water, they figured must have been artesian water. Okay. And then our house, it's pretty good, so and it comes from really, really, really deep, so we're figuring that may be artesian water. At my home, you know, the original house place down there on the farm, it was not artesian for sure, because it just would get too muddy or something else when it rained. Okay. Whoops, here comes Jackson. I think this is his first time here today, so let me get him in the books. Jackson's here. So that should have us up to 4, 6, 7, 8, 9, 10, 11 students. Let's see how many we got. Yep, we got 11, so good deal. I think we got everybody. So this produces an artesian, really, really deep aquifer. Somewhere up there, it may not have been so deep, but after a long, long period of time, it's really deep. Okay. And if you drill a well and then the water comes way up here, the odds are the pressure from over here, and their drawing is not very good. They're showing water here, but that's above the water table. That should bend off and just gradually go along here. There's the water table. So water comes up in the well this high. That means that's probably artesian water being pumped up from below. If, however, you get a place where your discharge makes its way to the surface below the water table, then that has what they call a flowing artesian well. Okay. Now, one way you can tell artesian aquifer, the water from that, is sense the temperature year round. If it's always right around 70 degrees year round, that's artesian water. And there was a place just below where my older brother on the north end of the farm had put his house there. Just within sight of that, there is the creek called McBean Creek. And on the other side of McBean Creek, at the bottom of a real tall hill, there was a flowing well, an artesian well. And how they knew it was artesian well, it wasn't like the creek water. It was much cleaner, neater, sweeter. It was just wonderful water. But not only that, it was almost always constant temperature. Now, when I was young, Vietnam was really going hard and heavy, okay, about the time I was in high school. So that meant that if you didn't go to college, you were going to Vietnam, almost. I mean, it was almost certain because the draft was in place. There was hardly any way around it. Unless you were going to college, then you got a student deferment for 4 years only, okay? Well, fortunately I got one, but I went through Navy ROTC because I knew I was going to probably go in anyway. I wanted to pick my way that I wanted to go in. I wanted to go in the Navy, not the Army, because my father and my uncle had both been Navy, and my older brother had been Navy, or was Navy at the time. So, so I had decided that, and well, various things. So anyway, but Vietnam, and this is before I went to college, when I was in high school, it was really going hot and heavy. And the Army figured out they had not trained their people to live basically off any kind of rugged terrain, and they needed to do that. So they rented the farm just adjacent to our farm that had been a pretty big cattle spread, and it was really hilly, rough, and not that inviting the land, but that's where they wanted to do, and that's what they did. And they set up their camps there. They lived in tents. They lived in, pretty rough. And they had to bring in all their water in big tank trucks. And I don't think that tasted all that good and wasn't all that great. Well, they found out that just down the road from there was that artesian well. And by the way, that water that they had there, it would get warm, tepid warm in the summertime, and it would be very cold in the wintertime. And that's what they had to shower with and everything else, and it wasn't all that pleasant, especially in the wintertime. But they found out that artesian well just down the road. They went over, found about it. No one really was using it then, but whoever owned it, they rented it from him, and that's where the soldiers went to take their showers, winter or summer. In the summertime, that water was 70 degrees. That felt greatly refreshing. And in the wintertime, it was near 70 degrees. It felt quite cozy and warm compared to the air temperature. So that was why we knew it was an artesian well. And there was another place down in the county south of us where they had Magnolia Springs. That was a flowing well. They had swimming pool there. But boy, in the summertime when it was really hot outside, that water felt awfully cold because it was artesian. When it's 90 degrees out, 70 feels awfully cold. So anyway, that's confined at a higher pressure, and if it finds its way up, you have some really good quality water, artesian aquifer. All right, freshwater as a resource. We talked about freshwater as surface water, freshwater as groundwater. And by the way, they did have a couple of examples in freshwater, um, and it's all just playing around with numbers. Uh, well worth a look, but you don't need to get too overwhelmed by it. There is a nice little concept supplied on page 612 or 24-7, talking about, is there room for water in the situation, whether it's stone. Sandstone will have more room. Limestone usually is a lot of room. Other rocks, granite won't have a lot of room. You know, you have to find gravelly type area around the granite. Okay. Then there's a thing on page 613 on deep wells. After doing some research, make a drawing to show the depth of the water table in your area and its relationship to local streams, lake swamps. That would be neat to do if there were a lot of wells being drilled. I don't think there are. Now, there is a very interesting little sketch here under freshwater as a resource. Let's talk about it first, and I'll go to this table. Now, freshwater, we gotta have it. No way around it. It's required for life processes and also modern industrial society. You gotta have fresh water. We cannot drink salt water. Does anyone know why? Seawater is about the same concentration. Oh, here's Drew here. Let me get Drew marked here. Good deal. We're getting a decent class size now. Okay, 3, 6, 7, 8, 9, 10, 11, 12. We should have 12 students here. See what we got. Yep, 12.
Afternoon, Mr. Charles.
Noon, how you doing?
My.
Good, glad you could make it. All right, we're looking at freshwater as a resource. We're in chapter 24. If you have the big book, it's on page 612. If you're, 613. If you have the smaller book, it may be listed as 24-8. I don't know how they numbered those. And that's what we're talking about now. And this is the slide. We're 8 pages into chapter 24. And by the way, today we're doing, getting started anyway in chapter 24. And then at 3:45 we'll stop and do the lab for chapter 23. And then I'll post sometime this evening the test for chapter 23. And then Thursday, hopefully we'll finish 24, but even if we don't, we will get far enough along so we will be able to finish on Tuesday. Then we'll have the lab for 24 on Tuesday. Then we'll have the test for 24 on Tuesday. And then I'll give at some point there, after I've put those out there, post the final exam. And then basically Thursday will be, you don't have to meet if you don't want to. I'll be here, but we'll talk about this on Tuesday. Certainly if you have questions on lab, tests, other things, that would be a great time to get everything turned in. Now, I'd love to have all your papers, research papers, by Tuesday. I'd love to have them sooner than that, but get them in by Tuesday, because Thursday is technically final exams day. That's when you start losing points for having them in late. So if you get them in today or tomorrow, that's still September, you get 1 bonus point. Anywhere from the 1st of October until not next Tuesday, the following Tuesday, that will be your just a score. After Tuesday, 2 weeks from today, after that Tuesday, you start losing points. So please get your papers in sooner rather than later. All right. So what we're talking about here, freshwater as a resource. Absolutely required. Yes. Surely.
So with the research papers, there wasn't like a specific page number, like how many pages we're supposed to have, was
1 to 2 pages. That's what is listed in the thing. Now that means pages of text. That doesn't mean all your headers and things like this. Pages of text. It's going to be at least 2 pieces of paper, but it will be 1 to 2 pages of text. Now I do want it double spaced, so it's not that much writing to do. Not as much as most of your English papers would be, but I just want you to get something that you're interested in, get outside the book, find material about it, write it up, turn it in. It can be about people, it can be about events, it can be about um, uh, applications, it could be about phenomena, it could be just about anything that has to do with physical science, which would be astronomy, earth science, weather, climate, water science, oceanography, plate tectonic, rock science, geology, geography, anything that does with anything we've covered. You pick your topic and write on it.
And do we turn it in the same way that we turned in our test, or email it to you?
Yeah, you can either attach it to an email and send it to me. You can attach it to a Blackboard message and send it to me. And if you can find a way to send it to me some other way in Blackboard, you can do that too. And believe it or not, in another class, in another term, I had a student who turned in most of her work by mailing it to me. I don't recommend that, but that's certainly okay. If you don't like doing the computer, or you can't do the computer and you can't get it easily done, you can even mail it to me. But that costs you postage, but that's why I don't promote that, but you certainly could. So yeah, any way you can get it to me, that'll get it to me. Okay.
Okay, thank you.
Surely, glad to. All right. Now, I was asking the question, why can't we drink salt water? We have all those oceans out there. Why can't we just drink that salt water? Well, basically it comes down to this. Salt water is about the same, and this is a weird word, osmotic potential as what your blood is. That won't work for us because you see, the water we drink basically is diluting the pollutants that are in our body. Now, I'm using those words very broadly here. When you digest your food, other things like this, there could be salts or other things that your body doesn't need from that digestion. Okay, so it needs to expel those. So it needs to have water. Remember, water is a great dissolver, a great transport mechanism. It needs that water to absorb those salts, the things that you can't use, the things that may even be toxic or something, and expel them from your body. Well, if that water has already got lots of salt in it, like seawater does, then it doesn't have any room to absorb anything else. Your body can't pull the water out of that because it's at the same osmotic potential as your blood. When you drink fresh water, then your body can use the water it needs to do things it needs the water for, and it can expel the pollutants into that water easily. It cannot do that with salt water. With salt water, actually, the more you drink, the thirstier you get, because now you're taking in more salts than you're able to expel, so you feel even thirstier, and you actually almost explode interior-wise, because you're just drinking all this liquid, but you can't expel it. Okay, it's a strange situation. So yeah, water everywhere, and all the boards of shrink, water everywhere, and not a drop to drink. That was the rhyme of the ancient mariner. Okay. Now, this is an incredible statement here. The average U.S. usage for water, for fresh water, is about 570 liters per person per day. And you might think, that sounds impossible. Now, a liter is just a little bit more than a quart, so I'm going to be very generous here and count it the same as a quart. If you take 570, got to get my calculator out. Oh, there it is right there. Okay. 570 and divide that by 4. That didn't work. 570, divide that by 4. That's 142.5 gallons. Probably closer to 143 or 145 gallons per person per day. I didn't drink that much, I promise you, okay? I didn't use that much for cooking. I didn't even really use that much for showering or flushing toilets or anything else. How did I use 145 gallons of water a day? Well, think about this. Now, this is average per person. Agriculture is what provides our food. That beef that you ate, the pork that you ate, the chicken that you ate, the vegetables you ate, the snacks you ate, all that was grown agriculturally, and when you were growing it, it was having to use lots of water to bring the nutrients out of the soil up to the plant so the plant could use it and form the production. The animals were drinking water and expelling water. Drinking what? They were using water, okay? Now, so 40% of that you use on average a day, you don't even realize because that's the food you eat. What is the water it took to grow the food you ate? And also the clothes you wear. This is a cotton shirt. That cotton was raised in a field having to have lots and lots and lots of water to produce the cotton that they made this, okay? 40% also was production of electricity. Believe it or not, no matter how you do your electricity, it's using water, okay? Certainly those hydroelectric dams, Lewis Smith Dam on Smith Lake, Gunnersville Dam on Gunnersville Lake, whatever the dam's named on Lake Martin and Logan Martin and Lay Lake and stuff like this, any one of them that has a hydroelectric plant, that's using water to produce electricity. Using the energy of the water, not the water itself, but you're still using that water. Oh, but what if I say, well, most of our electricity comes from coal or natural gas or some sort of production. Guess what? What is that coal burning to heat up? It's burning coal and natural gas, but it's heating up the water to make steam, and that steam is what turns the turbines that makes the electricity. Well, how about nuclear power? Well, guess what? That nuclear power is heating up water to make steam to produce the electricity. It's not going directly from radioactive, nuclear power directly to electrical power. No, it's using water to make steam to send through a turbine to produce the electricity. So 40% of the water, of that 145 gallons of water that you use a day, is producing the electricity that you're using. Each person is using. 10% industrial, okay? That would be, okay, I mentioned the shirt. Water was used to manufacture the cotton to do that, but then to get the cotton into threads, and the threads into fabric, and the fabric into shirts, that took industrial processes, okay? To make plastics, industrial processes. To make anything, industrial processes. So 10% is used for that. So basically, that's 90%. Not a bit of that was drunk. Not a bit of that was used to wash or do anything else. So only 10% of this. So that would be about 14.5 gallons is what you use a day. You don't drink 14.5 gallons, but when you take your showers, when you flush your toilets, when you wash your dishes, when you wash your clothes, when you do all those things added together, that's where that 14.5 gallons is going to. That makes sense. What you don't realize is this 90% that you are responsible for using. The food you eat, the electricity you use, and the industrial products that you use. Now, most of our fresh water comes from surface water. For instance, the city of Birmingham uses, I think, predominantly Lay Lake, okay, surface water. I don't know about Bessemer and some of the other areas, but I bet they do. I wouldn't be at all surprised if, say, Hueytown, if they don't use Birmingham water from Lay Lake, they probably use a plant off the Black Warrior River or somewhere like that. It's all, or not all, mostly surface water. Now, when I said the farm out in Georgia, guess what? That's groundwater. We're pumping that out of the ground. That's better water, okay? And here's why, okay? The surface water has more sediments in it, more stuff mixed with it, more bacteria in it, more pollutants in it, and it depends on precipitation to be collected in those surface areas, rivers and lakes and dams and stuff like that. Well, guess what? You got a lot of cleaning up to do. The first thing they do is run it through sand pits, okay? Just like the groundwater goes through layer after layer after layer, 100 meters or so of soil particles, but especially down deep when you don't have the bacteria and stuff, that all gets filtered out. So the first thing you do is filter it through usually sand, okay? And then they have to make sure they get all of the suspended matter out of it, the sediments. Then they've got to make sure they kill all the bacteria and viruses and fungal and everything else that's mixed into surface water, and filter out and separate out the pollutants, okay? So you have a lot of cost and a lot of, that's what water treatment plants are doing. They're cleaning it up. Now, out on the farm, drill down 250 feet, it's been filtered for you. Mother Earth has done that for you. That's good water coming out. We don't put any chemicals in it. We don't have to treat it in any way. Now, my older brother, because he gets sand, he has to have a sand trap and has to empty that periodically so it doesn't mess up his thing like clothes washer and things like that. So yeah, he has to do a little bit, but basically the rest of them don't have to do a thing, and we don't do a thing with ours. Now, most of the supply comes from surface water. That 40% that comes from groundwater for people who live out in the country or areas that they have to drill deep wells to get their water because they don't have that much surface water. That would be desert areas and stuff like this. That's relatively free of bacteria, suspended particles. That's good, fresh, and sometimes artesian water. Wonderful. However, the cost there is drilling the wells and then pumping the water up. You have to bring that water from very, very deep. That requires energy to do so. So here your cost is in cleaning it up. Here your cost is in pumping it up. Okay? So there's costs in every way. Generally, the pumping is a lot less expensive, I think, than the cleaning it up. But, and it tastes better too. Okay? All right, so there's fresh water as a resource. 570 liters per day per person, an amazing amount of water. That's about 145 gallons a day. Every one is using, not directly as water, but through the food they eat, the electricity they use, the industrial products they use, and then their use of water for cleaning and other things. Okay, must have talked too long because it won't advance. Let's see if I can get it to advance. Now let's move to the bigger, oh, okay, wait. I promised this and I didn't deliver. Back up one. Here is a pretty good table in your book, and this is, I can't read it backwards, average individual freshwater uses at home in the U.S. Now this is actual uses of the water, okay? Toilet flushing, I can't hold it up and read it at the same time. It's on page 613 in your book, 24-8. Toilet flushing, almost a quarter, 24.2%. Clothes washing, better than a fifth, 21.7%. Showering or bathing, that would be about 1/6, that would be 16.8%. Then just regular use from the faucet, that would be your cooking, your drinking, your everything else that you use it while just running, washing off your vegetables, whatever it is, that would be about, again, a little less than a six, 15.7%. And then, unfortunately, we have leaks and other wastage where it drips or the toilet doesn't close all the way or something like that. That's still close to 20%. So we use a lot of water, folks. And we are probably the world's worst water hogs that are out there. Okay? Most countries do a lot better job at conserving water than we do. Main reason we don't really have to. We have plenty, thank goodness. We're so blessed and fortunate to have good supplies of fresh water. So we don't, and they're relatively cheap. Birmingham is pretty expensive because you have to pay for all the stupid decisions that former politicians have made, and we're still paying off enormous debts from some of the stupid things they've done. But anyway, that's a different story. So we're ready now to turn to seawater. Now before we get there, okay, I forgot these pages. This is on page 614 and 615. An enormous blurb here, and this is water quality and wastewater treatment. It is quite a detailed description of what's going on. Look how much is there, and it goes on to the next page as well and shows you some of the schematics of about what goes on in treating it. Okay, why do we treat it? Well, like we said before, most of it's surface water. You got to clean it up, you got to filter it, you got to get rid of the bad stuff in it. All that has to be done. Now this is the other part, and it's a little sad. It may make you gross out, but hey, it's reality. We here in Birmingham are using surface water. We're using it, we're washing our clothes in it, we're flushing our toilets with it, we're doing everything else with it, washing our dishes, wastewater, everything's happening. Our water treatment plants, once they clean it up adequately, it goes back into the stream. Well, guess what? Downstream from here, maybe in Montgomery, maybe not Montgomery, but somewhere like that, downstream from here, they're using that same surface water from those same rivers, but some of the water we have used, they're going to be using. Okay? Well, guess what? Some of the water we're using, maybe Huntsville has already used it. Coleman has already used it. Somewhere upstream from us has already used that same water and then cleaned it up and put it back into the system. Hey, every bit of water that we've had on the planet since the beginning of time, most of it doesn't go away. We just recycle it. And sure, there's vast supplies in the ocean, but guess what? Even that is being recirculated, reused over and over and over again. So I wouldn't be at all surprised, and I think I've seen this somewhere, and I can't remember where it was, or I would pull it up, that you probably, if you think about how many molecules of water are in your body, I mean, a water molecule is incredibly small. There's probably trillions upon trillions of water molecules in your body. I'm just making a guess at that. It could be that one of those water molecules was at one time in, say, Abraham Lincoln's body, or possibly just pick someone far enough back in history, more than likely there. Even possibly somewhere more recent in history, but if you go further back, larger and larger likelihood it was in someone else's body. Almost all of the water molecules in your body have been in probably many other bodies, animal bodies, or whatever. We just reuse and recycle it all the time. Okay. Hope you're not too grossed out by that, but it's reality. Okay. Let's talk about, okay. They actually show some wastewater treatment here. I think that's a filtering bed, trying to get rid of a lot of stuff from it. Here is water being used for irrigation, for raising crops. I think that's what that picture is. Okay, water everywhere for all sorts of usage. So let's now talk 24.2 seawater. Again, more than 70% of the Earth's surface is covered with seawater. Now get these numbers. The average depth of that seawater is 3,800 meters. Okay? Now I'm just going to do a ballpark figure here. I think I'm about right on this. I'm not absolutely certain. But I'm almost certain that 400 meters is, no, wait a minute. Let me get this right. I'm doing this in my head, and I probably need to do more. Okay. Uh, 3,800 meters would be about 4,000 yards. Let's just round that and say it's about 4,000 yards. 1,760 yards is 1 mile. So we're talking something, the average depth of the seawater is more than 2 miles deep. More than 2 miles down, deep. That's on average. Now the deepest places are way deeper than that, because you have a lot of places that are way shallower than that. On average, about more than 2 miles deep. 30% of Earth is dry land, with an average altitude of only about 830 meters. Now that'd be about 850 yards approximately. So that's way less. Well, let's see. That's right about half a mile. Okay, right about half a mile, whereas more than 2 miles deep into the ocean. So guess what? There's more water. Water is deeper in the ocean, about 4 times deeper in the ocean than the mountains are in high. Okay, unbelievable. Most of the ocean is still totally unexplored. We have just little traces here and there where we've done enough to make any sense. Okay, I'm going to start recharging my phone because it's been discharging for a while now. Okay. Now, I've heard people say this, and I assume it's true. We probably know more about outer space than we do about our own oceans, because it's a tough place to explore. Because you get down 2 miles deep, there's not a bit of light, not a speck of light. You're in total darkness. What's more, the pressure on you would be so great you would be crushed. And they do not have but just very few vessels that will actually withstand that pressure and be able to take you down. But when you're down that low, what can you do? I mean, there's not a lot of options for what you can do, even in an exploratory. You can look, and you have to shine your own light, and you can only see a very small field of view. There could be all sorts of monsters you're real close by you can't even see. So it's just amazing. So let's look at the bigger picture. We have the oceans and the seas. What is an ocean? A continuous body of salt water covering Earth's surface. 3 principal regions. The Atlantic Ocean is number 2. It's in the middle. The Pacific Ocean is by far the largest. also with the greatest depth. The deepest part of the Pacific Ocean is way down there. And then the Indian Ocean is the smallest surface area of your three oceans. Those are your three oceans. Now, you may have heard people talk about sailing the seven seas, and you wonder what in the world they're talking about. Well, they sometimes will talk about the North Atlantic, the South Atlantic, the North Pacific, and South Pacific. They even made a movie like that. Then the Indian Ocean, and then they may talk about the Arctic Sea, the Antarctic. Yeah, they could talk about other things like this. There's only three major oceans: Atlantic, Pacific, and Indian. Now, there are seas. What is a sea? It's a smaller region distinguished by special characteristics. Now, again, if we're talking about it being seawater, then this would be salt water. But the Mediterranean is one sea. Gulf of Mexico is classified as a sea. Caribbean Sea is classified as a sea. They're mostly bounded by land. Other seas are almost totally bounded by land. So let's take a picture of what we're talking. Take a look at what we're talking about. Here is the Atlantic Ocean here. Okay, this is what they would call the North Atlantic. This is what they could call the South Atlantic. It's all the Atlantic Ocean. Okay. Over here and over here is the Pacific Ocean. They just had to split it somewhere, and so that's the biggest body of water. Why not split there? It's way bigger than the Atlantic. Way, way, way bigger. Here's the Indian Ocean over here. It doesn't extend nearly as far up, and a little harder to define what exactly bounds it, but it's the Indian Ocean. Okay, now your seas. Mediterranean Sea, largely bounded by land. Africa on the south, Asia on the east, and Europe on the north. And it goes through the Straits of Gibraltar there, okay, between Spain and Africa. Okay, there's also the Suez Canal here that connects it with the Indian Ocean ultimately. Okay, so that's the sea, mostly bounded by land. Here's another sea, the Black Sea, that feeds into the Mediterranean Sea. And here's another one, the Caspian Sea, that feeds into the Black Sea. And these are big enough that they are at least a little salty. Not as salty as the ocean maybe, but close to it. Mediterranean, you can't tell much difference. Okay, I don't know about the Black. Here, the Sea of Japan is bounded mostly by land, but it has access to the Pacific Ocean. Down here, they don't show it, but the South China Sea is here. They mentioned the Weddell Sea and Ross Sea off the coast of Antarctica. They are bounded at least on maybe three sides by land, but they're bounded also by ocean. The Ross Sea, again, bounded by some land, mostly by ocean. If you actually saw a picture of a globe, look at a globe, you'll see they're a little more defined than what they're showing here. The Bering Sea up here is bound mostly by the Aleutian Islands here and the land over here. So there's the Bering Sea. The Arctic Sea, some people will call it the Arctic Ocean. It really is more of a sea. Now, it looks way bigger than it is now because you see all this comes together up there and forms there. Gulf of Mexico was mentioned here. That's right here. That's classified as sea. Not completely surrounded by land, but largely surrounded by land. Caribbean Sea is right in here. It's bounded by Central America, South America, and a bunch of the islands here. Not completely bounded, but largely bounded. Hudson Bay is up in here. That would be a sea. The North Sea is right in here. The Baltic Sea is right in here. I think that's right. I believe that is. And there's several other seas on here they don't actually list, but they do list several. Okay. Largely bounded by land, but not maybe on every side. But generally salt water. See, there's no difference in the salinity of the Gulf of Mexico and the Caribbean Sea from the Atlantic Ocean. It's all mixed up really well. The Mediterranean may be a little less salty than the Atlantic because there's not much inflow mixing from the Atlantic. The Black Sea and ultimately Caspian Sea would be probably a little less salty as you go up. Okay, Sea of Japan, so much mixing here, yeah, you won't tell any difference there. And there's all sorts of other seas in here too. Okay, so that's the difference in an ocean, huge body of water, sea, much smaller body of water, sort of bounded mostly by land, but not necessarily all. So let's look at the nature of seawater. This is on page 618, okay? 24-13. One of the characteristics of seawater, it's salty. And the other word for salty is saline, okay? If you've ever dealt anything in the medical field, you know when you get fluids, so to speak, intravenous fluids, they mix it with saline, which is about the same concentration of salts that you have in your blood, and it's really not far off from the concentration of salts you find in seawater. But of course, the saline they give you is a lot cleaner than seawater. It's a mass of salts dissolved per kilogram of seawater. That's the term salinity. What mass of salts, that would be kilograms or grams of salt dissolved per kilogram of seawater. Okay. So basically it's going, well, we'll get into this in a minute. It does not change much with changes of water temperature. Certainly if water is very hot, it can contain more salt than colder water, just like hot tea, you can put more sugar in it than you can in cold tea. Okay, it does have a little bit, but it's not a major change. Most seawater is about the same salinity. None of it is saturated. Now here's where they've made their mistakes. Okay, what they put here is 35% and 32 to 36%. These are wrong. Okay, sorry about that. Here's what that should be saying. A percent is a part per 100, and these are parts per 1,000, not parts per 100. There should be an extra 0 here and an extra 0 there. It's parts per 1,000, not parts per 100. Percent is part per 100. This is parts per 1,000. I can't get that 0 to form without those silly things coming up there. It just won't write. It's aggravating. Okay. These are parts per 1,000. I got that one to write, but this one just won't write. Parts per 1,000. I almost got that one in. Parts per 1,000. I got it. It should have 2 zeros down there. Not parts per 100, but parts per 1,000. So this would be basically 35 grams of salt per every kilogram of seawater. Parts per 1,000. Kilo is 1,000. And that would be between 32 and 36 grams per every kilogram of water. Okay. Excuse me. The concentration is increased by evaporation and ice formation. Because guess what evaporates into the air? Water. Not salt, water. Now, sure, a little bit of salts make their way up, but not very much. It's the water is left, evaporated, that increases the salinity near the surface. Also, when water freezes, it's the water that freezes. It may trap a little salt in it, but it's not at the same concentration. So anytime water is freezing, it's making the remaining water more saline. Anytime it evaporates, it's making the remaining water more saline, higher concentration. Now, on the other hand, it's decreased by heavy precipitation. So if you have a huge hurricane sweep across large areas of the ocean water, it is going to, because it's carrying so much moisture with it, right under it, it's going to be decreasing the salinity, because heavy precipitation, again, rainwater is pure water. It's not salty, so you're decreasing the salinity. When ice melts, and this has been happening big time in Antarctica, in Greenland, in the Arctic, ice is melting way too fast. Those waters are becoming less saline, lower salinity. Okay? Also, river inflows. Right near the Gulf of Mexico, in the Gulf of Mexico, right where the Mississippi River comes out in Louisiana and pours into the Gulf of Mexico, not nearly as salty there as it would be out in the middle of the Gulf. Okay? So that means different kinds of animal life and other things will be there. So river inflow, because river, even though they're sort of polluted water, they're still not salty. It's mostly fresh water, so it dilutes the salinity there. Also, the proportion of ions is relatively constant. Okay, now sure, in some area where say there is some sort of a water plant, or industrial plant that's putting a high concentration of something into the water, shouldn't be, but if it is, then where that river outflows is going to have higher concentration of whatever those ions are. But generally, the proportion of ions are about constant. Now, water also contains dissolved gases. Anytime you have mixing with air, air is mostly nitrogen, next mostly water, oxygen. So, of course, your surface water is going to have high concentrations of nitrogen in it and high concentrations of oxygen in it. However, if you go deeper, now the plant and animal life is pulling the oxygen out of the air and putting more carbon dioxide into the air. So near the surface, you're going to have more oxygen. Deeper, you're going to have more carbon dioxide. Okay? And that's what it's talking about. Large amounts of carbon dioxide are also found in seawater. And the deeper you go, the higher the concentration gets, and that's why that carbon dioxide will actually form such high concentrations you start forming limestone. It comes out of solution because you have such high concentration of carbon dioxide. And limestone is carbonates, which is large CO3. Okay. Now, here are some of those ions. Now, in your book, they've made a couple of corrections where these are wrong. Oh, here's Andari's coming back in. Pretty sure I already have him on the roll. Yes, he is. So he must have got either booted out or had to go out. There's a few errors in here. I'll try to point them out to you. Now, when you think of salt water, salt is sodium and chlorine. And guess what? I'm going to go to the periodic table. We're not going to do this in this class, but sodium is over here in A, and on the same row but over here is your chlorine, Cl. Chlorine has more mass to it than sodium does. In fact, let me read you that. Chlorine will be 35.5 compared to sodium 23. So a good bit heavier, the chlorine, okay? So therefore, by weight, it has a higher percentage, okay? Sodium, next highest. After you get past salt, sodium chloride, they fall off big time. The sulfates, only about 8%. Magnesium, about 4%. Calcium, a little over 1%. Here's the first of the errors they have here, and I'll see if I can get this one corrected too. This is not, K is not a minus sign, K is a plus sign. If I can get my pen turned over in my hand right, this should be, there it is. That should be a plus there, a 1 plus, okay? Oh, come on, don't do that to me. it's trying to shut down PowerPoint. So I'm going to have to shut down PowerPoint and bring it right back up. So hang with me just a minute. Okay. Okay. All those corrections I made have been deleted now. So let me put them back in. This is parts per thousand, not parts per hundred. That's part per thousand, not part per, there, it did it again. It will not take it over here. Parts per thousand, not parts per hundred. And this potassium is a plus. Okay. Now, bicarbonate. Okay. This minus sign should not be down here with the 3. It should be up here. So I'm going to just, I don't know if I can do this. I'm going to try. I'm going to say this minus sign goes up here. Just like these other signs go up on top, not down here. Bromine, bromide is a minus sign, so that is correct. Okay, and this accounts for all but 11 hundredths of a percent of your materials dissolved in seawater, seawater. Okay. Now this isn't counting the gases. These are ions dissolved in it, not gases. Okay. Any questions on that? All right. This is illustrating what I was trying to say here. 35 grams of salt per 1,000 grams of salt water. Okay? In other words, your ratio of salts to water is about 35 per 1,000, not 35%, which would be 35 per 100. So that's why you need the extra 0 there. I'm pretty sure in your book it's listed correctly. This is on page 618, the last beginning of that last paragraph on the page. This is on page 24-13. They talk about this. Parts reported in parts per 1,000. The symbol, it's a percent symbol with an extra 0 on the end. The percent means parts per 100. This means parts per 1,000. Okay. And in your book, they corrected those things in the things dissolved. The potassium is a plus, and the bicarbonate, the minus sign, is up top, not down at the bottom. Okay. And they have a couple of examples there. If you're interested in doing them, you certainly can. It's just sort of playing around with the numbers some. Okay. Now, before we get into the movement of seawater, let me show you or point out to you a couple of other good blurbs. This is estuary pollution. What we mean by that is basically those areas near where freshwater meets saltwater, seawater. Okay, those are typically kind of called the estuaries. They're kind of a mixed area, and if you've got polluted water coming off the land going into the ocean, these estuaries can get very polluted. And these estuaries are incredibly important. We're just beginning to realize how important they are for cleaning things up, okay, for purifying things. And when they're polluted, boy, the pollution is rampant. And we've had a lot of evidence of this lately. I don't know if they mention it here. I think they do. Something, yeah, there it is. Different bacteria that pollute, like E. coli, estuary, I can't pronounce it, coli, that comes from basically our digestion process, the colon, it has a population of bacteria in it. They're beneficial for us, but you don't want it. You don't want it in your drinking water, okay? Because it's okay in the bottom part of your gut. That's where it belongs. You don't want it in the upper part of your gut. It doesn't belong there. It can make you very, very sick. Okay, so just because it's okay in one part of your body, it's not in another. There are other things out there. I don't think this is mentioning it, but things like your algae and things like this. The red, I can't think what they call it. Red tide, I believe, not crimson tide, but red tide, which is some type of a goodness, I can't think what you call it. I just named the name. Microorganisms that really pollute and do a number on the native species that are supposed to be there. All right, let's move then to the movement of seawater. Okay. The seawater is always moving. Okay, it's not just the waves are coming in. That happens. You can see that. But in the ocean itself, water is always moving. Always moving. Okay. Now, there's so much of it out there. The complete mixing is about once every 2 millennia. Okay, about every 2,000 years. That means in about 3 billion years we've been reasonably a planet, inhabitable planet. There's been about 1.5 million mixings, complete mixings of the Earth's seawater. So there's lots of it out there. Some of it's being evaporated, coming in as rainfall. Others of it's been out there in the ocean for an awful long time. Some of it's been cycled many, many times over. Now, 2 types of motion of these seawater. The first is waves. That's a surface phenomenon produced by disturbances. Okay. The second is currents. That's movement of water from one place to another, generally deeper. So the waves are usually a surface phenomena. A current is a mass movement underneath the surface. Okay, that's a generalization there. Let's start with the waves. These are the simplest structure of moving water. Okay, made up of moving crests and moving troughs. Here's the picture. Okay, the waves, the wind blows against the water and it sort of piles it up in some places, and of course where it piles it up in some places, it's evacuating it from other places. Okay, so this forms what we call 3 characteristic measures you can do of these waves. Okay, the characteristics are they have a crest up here, a trough down here. The lowest point in the wave is a trough. The highest point is a crest. Okay. Now the distance between 2 consecutive crests would be what we call the wave length. The wave's length between 2 consecutive crests. You could talk it between 2 consecutive troughs as well. That would be the same length. It's just that the troughs are usually gradual. The crests are usually rather pointed. Usually easier to measure that. Okay. Now, that's I got out of order. The wave height is the height between the lowest point, the trough, and the highest point on the crest. That vertical distance is the wave height. It's not the distance from here to there. That's something else. This is the distance from the lowest point in the trough to the highest point in the perpendicular distance to the top. That's the wave height. Vertical distance from trough to crest. The wavelength I just mentioned, the distance between 2 consecutive crests, or any 2 portions of a wave that are just alike, like this portion right here to that portion right there. Of course, that's hard to measure, much easier to measure crest to crest. Trough to trough a little harder because they're all this area. Where do you put the actually low area? Crest to crest is the easiest. And then those are both Distance measure. Height is a distance, length is a distance. The period is a time issue. The time between the passage of two consecutive crests. Let's say the wind is blowing from this way, blowing the waves along here. Here's the first crest here. It moves on out here. By the time the second crest gets to here, that's the period. The time between passage of two consecutive crests. Okay, that's the wave period. That's a time measurement. Wave height and wave length are length measurements, measured in centimeters, inches, feet, yards, whatever. Wave period measured in time, so many seconds or minutes. I doubt if you'd have any that long. Okay, excuse me, I'm going to have to do something with my throat. It's getting really raw. I've been talking almost non-stop since 8:30 this morning, so running out of comfort there, I'll say. Okay. Now, here are some characteristic trying to find the page on which these are located. Ah, here it is, page 621. The ocean waves, most of what you see on the ocean, most of what we experience is waves from the ocean, most of the time comes from the wind. There are some waves that don't come from the wind. We'll talk about those later. These are the waves that come from the wind. The characteristic of these waves depend on three factors. Now, they're coming from the wind, so all this is this. The first, how fast is the wind blowing? Now, I think I've mentioned it to you before, and I'll say it again. This time I may even write it down. Energy is what's the important thing here, and the energy that comes from motion is called kinetic energy, and kinetic energy, if you had the first half of the book, this would be old hat to you. 1/2 mv squared. 1/2 is just a number. Okay, m is the mass of the water. V is the mass of the wind, of the air, which isn't very much, but the velocity of the wind, that is the speed. And so you see, with a doubling of speed, you quadruple the kinetic energy. Tripling of speed, you're 9 times the kinetic energy. So the wind speed is a big factor on wave formation. Okay, the characteristics of wave. Number 2, the length of time that the wind blows. Okay, so even though the speed of the wind is important, and it certainly is, but if the wind has been blowing for a long period of time from the same direction, about the same magnitude, give or take a little bit, then the waves are going to be even bigger. It's kind of like, this sounds a bit bizarre, but it's really true, pushing off a car. Okay? If you've ever tried to do that, you know how you get it rocking. You push when it's going away from you, push when it goes away from you, push when you go, and after a while, you're then able to keep it going. The length of time that the wind's blowing is kind of that same concept. The wind's been blowing a long time, it just builds up and builds up and builds up the wave characteristics. And then the third of these is a distance factor, the distance that the wind blows across the open ocean. Now just think about this, folks. I don't know why my phone just keeps ringing like crazy. Okay, fetch, the distance the wind blows across an open ocean. Think about this. Think about how massive the Pacific Ocean is. I mean, how big? That wind can blow for miles and miles and miles across that ocean. And as it does, if it continues doing that way, just builds up more and more. It's kind of the same concept of the time issue, but now it's a distance issue. So that's the fetch. Now, what you get from the three of those is a complicated mixture of wavelengths and wave heights that are generated by the waves. Because guess what? The wind speed is always constant. The time that it's been blowing at a certain speed is not always going to be the same. And the distance over which it blows, it may run into an island here or something else there, or the wind may deviate because of weather issues. Yeah, okay. So it's a complicated mixture of wavelengths and heights are generated. The smaller waves tend to dissipate from friction in the water. And you might not think of water as having friction. It does. If you have ever jumped into a swimming pool, thought you were going to be diving in, but wound up flat and hit the water like this, you know that's called a belly buster. You know that water has friction because it hurts like crazy. Okay, water does have friction. Okay, so the smaller waves, generally, if the wind speed is changing, the wind distance is changing, the fetch is changing, they're going to be all mixed up, and they're all basically going to dissipate due to friction in the water. Okay, the larger waves last longer, they tend to travel faster. Eventually they coalesce into a swell. Okay, and this term is defined, I think, on the next page, top of page 622. Now, when I was in the Navy, we usually did a report once a day that you just summarized how things were going. And one of the two of the things that you summarized, and you had things you were able to measure, wind speed and blah blah, temperatures, all like that. But then the other thing you observed was which direction the swells were coming from. Those are the big rolling things that comes after a long time of the wind blowing in the same direction and stuff like this, as opposed to the waves, which are usually shorter term. So the waves could be coming this way, but the swells coming that way. And you could look out there and see and tell the difference. The swells are big, rolling type phenomena, and the waves are little choppy things. Okay. So if the larger waves last longer, travel faster, eventually coalesce into these swells, especially if you've had a long time wind blowing at nearly the same speed over large distances fetch, then you get swells. Then later the wind changes, and then you get waves coming from a different direction, but your swells are still coming from that original direction. That's what you're looking at. Very complicated mix of components here. So let's look at those swells. The swells carry energy, but basically do not move much water. I don't know if you've ever fished with a bobber, cork or plastic bobber. Now sure, you got a weight at the bottom, but even if you had nothing on there but the line, that bobber basically goes up and down like this, but it doesn't really get pushed back and forth. Maybe a little bit back and forth. It rocks back and forth a little as the water goes up and down, but basically it doesn't move any. That's what's happening with swells. It carries the energy of the water, but doesn't do much transporting of water. Waves, on the other hand, are actually usually moving quantities of water. Swells carrying the energy of that motion, but not transporting the water itself. Now, the individual particle motions are basically circular. Like I said, they go back and forth some. So let's say a swell comes along, and this bit of water here gets lifted, pushed ahead, lifted this way, and then when this one falls, it goes back like this and basically forms circular motion. Stays right there at the same place. It goes this way some, up and down some, right and left some, but basically it's just staying in the same location. Okay? Now, the diameter of that motion is equal to the wave height. If you go back here, the wave height is the difference between the trough and the crest. That's your diameter of that circular motion of water that you have. And here you'll see a picture of it. There's the wave height, and that is also the diameter of the circular motion of the particulates, the actual water particles, molecules. They just go in that little circle thing. Now, you go down to about 1/2 of a wavelength, and you wouldn't think this had anything to do with it, 1/2 of a wavelength, and you get down to the point where there's no more motion. So you see this motion is just back and forth, up and down, back and forth, up and down. It's circular. No transport of water from here to here. Okay? A wave could have that, but the swells do not. Now, most of the time the swells are not pointed like this, but they use the same illustration they had before. They would be rounded at the top and rounded in the crest. So you just have to judge from that. But definitely when you get close to 1 wavelength down, you have absolutely no movement at all. No circular motion, nothing. It's just at rest. Now, my throat's hurting. White caps are formed when the top of a swell is toppled by a strong wind. So let's say we do have our swells that are built up some energy here, and they have gotten sort of pointed like this as opposed to rounded. Pointed like this, and then wind comes along and blows that top over. That is called a white cap, formed when the top of the swell is toppled by a strong wind. Lots of tops. Oh my goodness, how could it be? Okay, I think we pretty much finished this slide. Let's see what the next one is. Shore effects. Let's see where we found that in the book. I'm going to say, yeah, we're on page 622, probably the first column. It's right there. I think I've got a mark already there, so that's where we'll end today. See how far we got. There, we got to 24:17, and we've got to go to 24:23. So we got more than half of the chapter covered. I'm pretty sure we will finish the chapter on Thursday, probably with plenty of time to spare. So plan for Thursday again, like we've done the last 2 Thursdays. Take advantage of those times to catch up any other labs and tests that you may be missing. Or work on your research papers, hint, hint, okay? And don't let that time go by unused. Okay, so we'll call it quits there for the class part. Let's move to the lab part. Now, I don't know if I have a copy of this lab or not. Let me see if I do. Some of these I make up and then forget to make myself a copy, so I may have to, like I've done before. Let me just see if I've got it, because I know I've been counting on y'all having it, and I found out later, I had that, you know. So let me see if I have that this time. Nope, I don't see that I do. Okay, so again, I'll be counting on y'all to help me, but I'll show it on the slide. Okay, so let's get out of this. Do y'all need to take a little break? Yay or nay?
I'm good without a break.
Okay. I want to keep on going then, huh? If anyone needs a break, I don't mind doing a quick one. Okay. Got to see where we are. I'm in the wrong class here. Let me get out of this class, Math 113, and get over into Physical Science 111. Okay. I'll scroll down. Not too, oh, no, not quite there yet. There we are. So here we are, Physical Science 111. That's us. I'm opening it now. This is Blackboard Ultra. And why is it not opening? I don't know. Things have been weird today. I click on something and nothing happens. I get over here, it says JavaScript void. And I know that has to do with some sort of machine language, I think, or something like that. And it seems like it holds us up then. Yuck. I don't know if it's that I'm screen sharing or what. Oh, here we go. Wait, Gerald's come in. Was he here already? Yes, he was. So he's just coming back. Okay, well, I thought that was someone. See how many we got now. 12 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, got everybody. Ah, it finally is opening. But now it's resolving hosts. You would think, I don't know. I don't know if I've got 5 bars of internet, it says, so that should be good. I don't know why things are taking so long to open. My wife says it's something to do with this computer, this is not more than a 2-3-year-old computer, and it certainly should be doing much faster than what it does. She thinks that probably they loaded this was a computer they used in training for Blackboard and other things like this, and they probably got so much stuff loaded on it or stuck away on it they don't even realize is there, that it just is incredibly slow. She can't stand it. Her computers are older than this one, and hers open right up. And I doubt if they're that much more powerful, but she hasn't figured this out either, and she's pretty good at them. So we're waiting for Blackboard Learn to open. I just love Blackboard. It's one of my favorite tools of all time. A couple of weekends ago, I had to spend almost the entire weekend listening to 4 presentations by various vendors selling us on their course management packages. Blackboard is, of course, one of them, but the others were Moodle and Canvas and one called DS2. I wasn't familiar with that one, but they all sounded much swifter and easier to use than Blackboard. Blackboard was a clunky old device here. Now, they've tried to, it's sort of like, now again, I'll use my wife. She says when the big box stores started to try to go online with stuff, well, now I'm having to log back in. That's probably one thing that was taking so long. Okay, this is so much fun to log into it too. Sort of like the big box store that try to set up things that you can shop online, and how much clunkier they are than things like Google or Amazon or something like that, that was developed to be online. I think Blackboard is the same thing. I believe it was it's just a clunkier old version of way of doing things than what the newer faster, less bulky things to do. Well, now it won't load. This may have some of the same issues of my screen turning green earlier. I think there's something wrong with the systems. Like I said, I've got what says good in. Oh, finally it's coming. Okay. There was the stream, and I'm not going to mess. Oh, no, we're not doing stream. So let's go down and find our class. We were there before, and then it froze up. There we are. This one right here. Okay, was that somebody else coming in, or was that just because I happened to swipe near? Yeah, I just swiped near, I think. Okay, go to the weekly activities, and I'm going to have to move y'all out of the way. Matthew, you're in the way again, so let me get you out of the way here. Okay, so let's open our weekly activities, assignments and activities, and go down to week 7. Out of 8, folks, we're on the short rows now. Week 7. Now, I didn't get all the things done that I normally do by now because we were out of town this weekend and I couldn't get everything done. Your overview is mostly done but not finished. Instructional materials, not finished. I meant to take this out because this is not something you see anyway, so I'm going to get rid of it now. There is no class discussion yet. If you want anything, I'll leave it out here, but once the week gets over with, I'll remove it. Week assignment, that's probably where your lab will go. I don't think it's in there now. Let's just look and see if it is. I don't think it's there now that I think about it. No, I haven't put anything there, but that's certainly where I will put it later. I've already passed. It's under instructional materials. I said this isn't finished. It's not finished, but I put everything we needed for lab today here. So that's where it is under week 7, instructional materials. Okay. There was the PowerPoint slides we were using today and we'll use again on Thursday. And I haven't done this stuff here. I've got to update this. But here's the lab. Here's the site we'll go to. This is the link, and let's see if it'll open. No, it won't, so I have to take this. Okay, what I'm going to do, I think I'll open this first. No, I'll open this a different way. Okay, let's take this, but there's your lab. This is what you're going to fill out. So if you don't have it already, get this. PHS111 Lab 8. It's a Word file. Okay. Now I'm going to take this this link here, and move it to my, oops, I meant to copy it. Sorry. Okay. Copy that. I'm going to copy it here. Trouble is y'all are in the way again. Oh, Amari's here. I hope he hasn't been waiting long. I moved y'all out of the way and it was blocking it. I think this is the first time Amari's been here today. So let me get him in. That gives me 3, 6, 7, 8, 9, 10, 11, 12, 13. So I should have 14 with me. Yep. All right. Okay. Sorry this is taking so long. Okay. I'm going to paste that in here and hit return. Now you'll probably recognize this. We've been here before. It's resolving host. Everything's taking forever today, so don't get impatient with it. I get impatient really easily with this, with Blackboard and with Microsoft products and with a lot of things like this, but hang in there. Down here you see it's resolving hosts, so it's having to go through all this. And it'll open up one of these days. And I want to be doing other things, but I'm afraid if I do anything else, it'll disrupt this and it may take me longer to get it open. So still resolving hosts. I don't know why everything's taking so much longer today. Again, it may have something to do with why my screen went green in an earlier class. Okay, here we are. And this, hopefully you'll recognize. Now I'm going to pause this for just a moment. What I'm doing there, I'm going to open the file. Come on, where is it? I'm going to just go on and minimize this. Oh no, I need that anyway. Okay. Goodness, here it is. Okay. I'll be there in a minute. Okay, this is Lab 8. All right. There is what we're going to be answering. And it says go to week 7 instructional materials. That's where we are, tab in Blackboard. Click on the laboratory simulations link. That's what we did. Click on the simulations tab and scroll down to and click on the greenhouse effect. I think I left off of something there, but I'll point it out to you. Click on the triangle, blah, blah, blah. Once there, stop. Okay. So this is where we're heading, and this is how we're going to get there. So let's go back. Oh, you couldn't see that, could you? I'll show you that one. Sorry, I thought it was just there screen sharing and then it quit. This is what we're talking about. Go to week 7. We've gone there. Instructional materials tab. We've been there in Blackboard. Click on the laboratory simulations link. We went there. Click on the simulations tab. We haven't done that yet. So we're going to pick up when we go back to it, the simulations tab, scroll down and click on the greenhouse effect. Now, I think it left off something in the middle here, and I'll tell you what that is. We'll click on the triangle and go to in the circle to go to the simulation. Once there, stop with the button in the bottom center. So you'll see that too, I think, if I can remember that much. So let's go back to screen share here. And where was the simulation? I think that was it there. Yes, there it is. Okay, so you see where we are, folks? The FET, Colorado, blah, blah, blah. Okay, go to simulations. Here's the part they left out. Go down to Earth Science. I think that's what the part they left off, that I left off.
They did, yeah, Earth Science.
Go to Earth Science, click on that, and it's resolving host again. Sorry about that. Okay. I thought it was resolving host. It's just hanging there. So let me click again. Sometimes I get too impatient. Okay, resolving host. It's back to resolving host again. So I'm going to keep it on this for a minute. Sorry this is taking so long. I don't know if it's that everybody's on the internet these days, and even though I got a good signal, everything is just taking forever. Still resolving host. Aren't computers supposed to speed things up? Have any of you been able to get on it yet? Are you trying to? You are, under Earth Science.
Yes, sir.
Okay. I'm not doing anything wrong, am I? It's just slow.
Yeah, it may be on your server.
Yeah.
It could also be because you're streaming.
What's that?
So, like, it could actually be your computer itself.
Okay. I think it's finally responding now. Because my screen went white. Boy, I'm going to forget what I'm supposed to do by the time it finally gets it done. Okay, it's under Earth Science. I can tell that now from up here on the command line. So it's still resolving hosts there. There must be something wrong. I mean, but with 5 bars, you would think it would be moving faster than this. But I'm not on a 5G, so that may be part of the problem. Those of you who are on it already, are you on 5G or what are you on?
Yeah, I'm on 5G.
Okay, that must be
I
it.
only have 2 bars, but it's working.
Yeah. Well, I think mine is trying because it's moved to Earth Science up here and resolving hosts down here. So be patient with it. Don't say this isn't working. It's just working slowly. This is the same place we came for the plate tectonics lab. So, but note on your instructions there, I left off to go down to Earth Science and click. I hope you'll have better luck than I. The lab's not going to take that long if it'll ever start. Come on. This is the kind of stuff that just eats up my day. I'm usually a pretty patient person, but when things like this just for no apparent reason take forever to do. Ah, here it comes. Still resolving host, but at least I got PHET, whatever that stands for. Physics something or another, interactive simulations from the University of Colorado at Boulder. So I got that on here. But I thought, well, this was here before, but it wasn't under Earth Science. Well, now I've got 3 dots here in the middle of the page that are moving, so that's something new. Boy, we take great pleasure in little things, don't we? I think my hamsters are tired, the ones that are running around powering this thing. They must be taking a break today or something. Okay. In fact, most of the time this comes up so fast I didn't even know it had these 3 dots. This is the first time I've ever noticed them because it's taking so much longer today than it usually does. Ah, here we go. Now, what we do now, I'm going to move y'all around again. Matthew, you're in the way. Okay. So, let's go down until we find, I'll see it when I recognize it. There was plate tectonics we did earlier. Greenhouse effect. There it is. Okay. Click on that one. And then go to the triangle in the circle. You see where my thing is? Click on that. And now it's resolving host again. But this is moving a little faster than it did. Okay, have y'all been there for a while? Man, this is like watching paint dry or water boil, trying to watch a plant grow. Well, at least it's sparing my voice a little bit because I'm just sitting here now. Okay, I'll regret this later, but I'm going to move James again. Okay, yeah, we're still on greenhouse. I sure hope this is the right one. It seems like there were a couple of labs that were similar. I hope I got on the right one here. It looked like the right one. Does someone have the lab open?
Yes, sir.
Okay, does it say go to the one that say greenhouse effect?
Yes, sir.
Okay.
It says, yes, greenhouse.
Okay.
Greenhouse effect. Click on the greenhouse effect, yes.
Yeah. I guess I could go back and forth between that, but I'm afraid. Okay. Cheer PJ runtime ready. I have no idea what that means. I saw Cheer PJ right up here, and I didn't know what runtime ready is. Everything is taking so long today. These are the kind of things you think, if I just start it all over with, would it go faster? And then you knock everything down, take it down, start it up again, and find out, no, it didn't make it go any faster. And you think, I've wasted all that time. So, I don't know. It's encouraging that y'all have gotten there sooner, but so now I'm dropped a bar. I'm now only at 4 bars. But I think mid-afternoon is a very, very busy time. They're still active on the East Coast. They're active in the Central Time Zone. Mountain is really going hot and heavy now, and Pacific is hot and heavy. So I bet you the whole thing is just, well, y'all are on though. I'm not. I don't know why. Going back to, oh, look at this. Now I got 2 circles that are playing with each other. Well, that lasted a little while. Greenhouse effect is starting up. Usually this happens so fast I don't even see these individual slides. I'm sure they all pop up there so fast. Okay, here we go. Here we are. Okay. Now, I think the next instruction said move this to slow, wasn't it? Or stop. I think that's what it was. Stop it. Okay. Now, read me the first instruction there. I think that was the one. That button in the middle down here at the bottom that now says play, it was 2 vertical lines and that was stop. Okay? We've got, just to take a look here, we got sunlight photons. That's energy coming from the sun. Those are the photons of energy coming down. They're sort of yellowish like the sun, and they're coming from up high. Okay. Later we'll see infrared photons. That's once the photons have reached the surface of the Earth, gone through the atmosphere, they lengthen in wavelength a little bit, lose a little bit of frequency, and now they become infrared photons. Those are what trap the heat on the surface. This is the sunlight photons, the energy coming from the sun in electromagnetic radiation. When they get to be infrared photons, it's this coming from the same source. I mean, they've been altered here, and that's when that's what creates the greenhouse effect. Okay, Now it says greenhouse gas concentration. This is today. Does it say start with today, or does it say start with the, I think it starts with today, doesn't it?
Yes, sir. It starts with today.
Okay, what's the, okay, read me the things, because I don't have it up. So,
Atmosphere during today,
okay.
during 1750, and during Ice Age.
Right, okay, no, I can read this. What is the first question on the thing?
That's the first one.
Oh, wait. Let me see. All right. Okay, yeah. It says record the initial conditions, and what you do is put A here for today. That's where we are. And then the greenhouse gas concentration is which one? A, B, C, or D? A, B, C, or C. And then the greenhouse gas concentrations, that's what we saw in the box. So that's where we're starting here. And like it said, click on the, once there, stop the button at the bottom center, and that's what I did. Okay? So what you put down is, since we're doing today first, you'll put A here. Okay? And let's keep this in mind. Let's go back to, here it is, this one right here. All right, so today was A, and it said greenhouse gas concentration, which color bar? Green. You see that under greenhouse gas concentration? You see what I'm talking about?
Yeah.
Okay. Then it says greenhouse gas composition. Water, 70% relative humidity. That's what you put by H2O. CO2, 388 parts per million. That's what ppm stands for. Methane, that's CH4, 1.843 parts per million. So it's not a lot of methane. NO2, that's nitrogen oxide, is 0.317 parts per million. So those are the four greenhouse gas concentrations that we record. And then it says put down the initial temperature, right? And that is minus 16 degrees Fahrenheit. Now that's awfully cold, but this is just assuming no photons from the sun have gotten here yet. We see 3 of them coming in here, so that's where we're going to start. Okay, what's the next thing it says? By the way, if you're when you pull it up, if you're in Celsius, you want Fahrenheit, this is where you change it. Okay, click on thermometer here, Fahrenheit here. I figured y'all were more used to that. Okay, now
Wait, so what's the temperature?
minus 16 degrees Fahrenheit. You see the thermometer over here on the left?
Yeah.
Figure out why mine is saying 60. I don't know what I'm doing wrong.
Okay, wait, you must let yours go longer. What you can do is reset all.
Oh, okay.
Okay, let's go back and reset all then. We'll all start at the same place. Reset all. Okay, wait one. Okay. Reset all settings, yes. Okay. Now, hit this stop button down here. No, I'm sorry, it was already stopped. Okay. So here's what we got. The first one was atmosphere during, and it had A, B, and C. A was today, B was 1750, and C was Ice Age, right? We're in today. So number, whatever that one is today. A, right? Next question was what your greenhouse gas concentration was, and we're in the green. And what that means is greenhouse gas concentrations were lots of them out there, okay, as opposed to none. We're in the middle, but in the high part of the middle. Lots, toward the lots. Then the next question, didn't it say what are your greenhouse gas composition? Okay, water vapor was 70% relative humidity. Carbon dioxide was 388 parts per million. Methane was 1.843 parts per million. Nitrogen oxide was 0.317 parts per million. Where thermometer is on the Fahrenheit scale and the temperature now says -9 degrees Fahrenheit. So if you put something else down and you want to do -9, that's fine. Whatever it starts, wherever it started for you. Okay, and what's the next question? Does it say start?
Okay, it says start the simulator using the triangular button on the bottom center.
You see where I am now, my cursor? That button right there. Okay, we're going to start it. Okay, and what does it say do once I start it?
What initially happens to the temperature?
Okay, we're going to look at the temperature scale over here once I start. So let's start it. And you see the temperature actually is dropping. -12, -13, -14. But here comes photons from the sun. And when they start coming, you see this is still dropping because it's not heat yet. But you see here are some infrared photons, and when they start coming up, look at the temperature. It's increasing now. And when these reds start really bopping around, that's when our temperature goes up. Okay?
So what are the first photons?
The first photons were the sunlight photons. And then
Number 6.
is it okay? I don't have it in front of me. Okay, and then you have the infrared photons are coming up, and you see they're generating basically from the earth. It's the same energy coming from the sun, but it's lengthened in wavelength and become infrared. They will head back up, but they bounce around a lot. They come back down and then go back up. So you see your temperature keeps increasing. What else does it say?
After a time, which photons are greater, which would be infrared?
Yes, now it's infrared. After a time, the infrared are greater. At first, it was sunlight photons. Now,
what seems to be the equilibrium temperature?
Okay, we're now going up to 55 Fahrenheit, 56. We'll let it go for a while when it sinks. Oh no, is that 56 or 66?
56.
Okay, it looks like it sort of reached its thing around 56 or 57. Okay, so that seems to be. Is this somebody else coming in?
No, it was a question.
Okay, all right.
5 is dropping.
Number 5 is dropping.
I was answering a question in chat. He said
Oh, I see.
Happens to the temperature, it drops.
Yeah. And let me sort of explain to you what's going on there. The amount of radiation we get from the sun would not support life as we know it. If we didn't have our atmosphere acting as a blanket, trapping the energy from the sun, we would be too cold of a planet. Okay? Venus is quite hot, but they have even a thicker atmosphere, but we'd be too cold. But our atmosphere acts like a blanket for us, and these greenhouse gases are indeed beneficial to us up to a point. But when we get too many of them, we get problems. Okay, so it does seem like we've reached equilibrium temperature around 55 to 56 degrees Fahrenheit. What's the next question? Was there another one?
Stop the simulator.
Okay, so that's this.
Reset Alt-Tab button to the right. Click yes, and then click on atmosphere during 1750.
Okay, so we're this button in the middle, the two vertical lines, hit that, and that pauses. It stops the simulator. See, there's no more bouncing around going on. Okay, now I do want you to do this. Notice what we see here. We see satellites. That's today. We have weather satellites. We have all sorts of things up there. GPS satellites. This is modern day. We have big businesses. We have homes. We have, this is what you see. Okay? Now what we're going to do, you said reset first. So you see this button over here that says reset. Reset all. Reset all settings, yes. Okay. Then we're going to click the button that says 1750. You see that one? And when we click on that, notice that this greenhouse gas concentration moved to purple, and that was a little bit fewer greenhouse gases than what we have now. What else do you notice happened to your picture?
Everything's gone.
Well, just about. Certainly the satellite's gone. The big businesses are gone. What the paved roads were gone. Now you have just a farm here, basically. Very much an agrarian society. Okay? Let's see what our greenhouse gas concentrations were. Relative humidity still around 70%. That didn't change. How about our carbon dioxide concentration? Was that any different? About half.
No,
Well,
a little bit. It was 388.
388. Okay, I was thinking 588. So it's dropped about a third. Okay, maybe not quite. Better than a fourth, less than a third. Carbon or methane concentration, I think that dropped a little, didn't it? Did it?
It was 1.8.
1.8. So it's about half of what it was. Okay. Okay. And nitrogen oxide. What was it before?
It was 317.
Okay, so it's dropped to about maybe close between a quarter and a third also. Still on third, okay? Ooh,
What was the initial temp? 56?
well, that's the thing. That didn't reset. It was supposed to have.
Okay, but we've skipped some questions, though.
Oh, we did. Okay, what were they?
Number 9 question was, what disappeared from the sky? We know the satellite disappeared.
Okay.
And would we say the protons disappeared?
Okay, no, that's enough. The satellite disappeared.
Okay. And then it said, what changed on the ground? And that would be
The big buildings.
buildings.
Yeah, the big buildings that were over here, the industrial looking buildings, skyscraper type thing. The paved roads disappeared, and a lot of the houses disappeared, certainly the modern houses. And what do we left with? Basically an agrarian society, a farmhouse. And this may be a dirt road here. Okay, I'm guessing it wasn't paved. The other one was paved. Now, what I'm surprised at was,
Okay, is the greenhouse gas concentration green or purple?
purple.
Purple, right?
Yes, it's purple. Okay, it's not dropped much, but it did drop a little bit. Yeah. Okay, that was B, wasn't it?
Yes, sir.
Okay. Now, what I can't understand is why the thermometer when I reset, the thermometer should have gone back like it was before. Maybe when I start, it'll drop again. Okay, were there any other questions before we started again?
Yes, sir. Can you wait just a little longer?
Say again?
Can you wait just a little longer?
I couldn't quite make that out. Wait a little longer, is that what you said?
Yes, just
Okay.
a little bit.
Okay, yeah, sure. Got all the time in the world. It's only 4:28. We go to 5:45. We got plenty of time now that it's finally started. For a while there, I wasn't too sure.
So, the question on 13,
Okay,
would that be 56?
okay. What was that? Equilibrium temperature?
It says the initial temperature.
Okay, let's wait till we start it and see what happens. I think when we start it, it's going to drop. Okay, is everybody up to the point of starting the button again, simulation again? Okay, see, I don't have the paper in front of me. Let me go and see what I can find.
H2O was 70%. CO2 was 280. CH4 was 0.73.
See, here they are. If you've got my screen on the thing, here they are right here.
And N2O is 0.270.
Those are parts per million, ppm.
Yes, ppm.
Relative. What did you say? Okay, what other question? I don't understand.
I was saying for number 11, I thought I had that one, but I had number 12.
Okay. Okay, any other questions before we start this one?
You got purple for number 11? You got B?
Yeah, I got that, yeah.
Okay.
1750 was the one before that, probably. Now, don't put the initial temperature until we start the simulation. Is this somebody else coming in? Let me see. Nope, I think we got everybody. Should be 13 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got it. Okay. Okay, ready to start the simulation? Okay. Let's start it. Yeah. What's the initial temperature? -8. And it keeps dropping initially. You see photons from the sunlight, photons coming down. These are probably questions you have. A few of them are coming down. And finally you see a few reds start coming up. But they don't seem nearly as active and aggressive as the first ones were. I don't know if you noticed that or not. Okay. Our temperature, by the way, has started increasing again. Okay, after a while you get more infrared photons. Okay, so that was the same as before. But it just doesn't seem like quite as many as there were before. Temperature is still going up around 40 degrees Fahrenheit, 41, 40, oops, seems like it slowed down here some.
The first photons that dropped was
The sunlight photons, just as before. What was the next question?
number 14 is increased. Temperature increased.
Yes.
The first photons was sunlight, and after number 16, after a time when photons are greater, is infrared. Correct?
Right. Yes.
Number 17. What seems to be the equilibrium temperature?
Okay, let's see what we're up to now. It looks like we're 54, 55. Was that about what it was before? Or was it a little less? Huh?
56.
Okay. Seems like it's about the same. So not that much has changed, it seems like. They're indicating it might be. Okay. Anything else?
So we're going to stop the simulator.
Okay, stop the simulator. And
We're going to the ice age.
okay, let's reset all, and then answer yes. Reset all settings, yes. Okay, now it went back to today, but we go to ice age. Okay, click on the ice age. That was answer C, I think, or something like that, wasn't it? Okay, was there a question? Because something popped up. Okay.
Oh, okay. I didn't see the question.
Okay, and then the greenhouse gas concentration has dropped down to blue. And today we started with green and then changed just a little bit to purple, now dropped pretty drastically to blue. We're in ice age. The H2O they don't even have, because we don't have any way of guessing what the relative humidity was then. But CO2, look at that, 180 parts per million. That dropped a little, didn't it? Okay. Methane dropped down to 0.38 parts per million. That dropped also, didn't it? A little bit. Seems like it did. I'm not writing this down. I'm counting on y'all writing it.
Methane.
Yeah, CH4.
H4 was 0.73.
Yeah, now it's 0.38, almost half of what it was. And then nitrogen oxide is down to 0.215. I believe, what was it, 217 before, 270 before, or something like that? Or okay, so it's dropped also. And I think we dropped a student or two. Okay. All right. Now, what's the next question? Did it talk about the landscape?
What was the initial temperature? Did we get that?
Okay, we haven't gotten there yet because that's when we start the simulator. Let's answer the other questions first.
So it says start the simulator using the triangle button on the bottom.
Okay, we didn't talk about that we no longer even have a farmhouse. We have snow in the background. They didn't ask that question. I didn't ask that question.
Oh, okay. You all jumped. Okay, wait a minute. What changed on the ground?
Okay, that's it.
Yeah.
You lost the farmhouse and you got a bunch of snow. In fact, there's no obvious inhabitation now. The ice ages, probably everybody moved south that could. They wiped out if they couldn't. So, wasn't any.
Greenhouse was blue, y'all. Blue bar.
Yeah, greenhouse gas concentration was blue bar as opposed to green or purple. Ice age. Y'all got the greenhouse gas concentrations, right?
Mr. Power,
Yes.
are you recording this?
Yes, I am.
Oh, okay. Just make sure.
Okay. Can everybody, I don't know if you can see this, but yeah, since I am recording, you can go back and view it later, but it'll probably be late tonight before it gets up there. So, actually, I've had some nights at 10 o'clock at night, it's still not loaded. So, I can't guarantee it'll be there tonight, but it'll be there in the morning for sure. Okay, any other questions before we start the simulator?
We needed to go back over number 12 for one of them.
Okay, what's number 12? I don't have it in front of me.
Number 12 is, I hope you're ready, H2O 70%.
Okay,
CO2 280. CH4 0.73. And nitrogen oxide 0.270.
okay, that was for 1750.
Yes.
Okay.
That's for number 12, 1750. Yes, sir.
Okay. Here, if y'all can see the screen, I can do it here, and you can see it there too, since we aren't doing anything. Oh, it won't let me do it until I reset, I guess. So let me reset again. Well, it seems to have hung up on me. Want to start? Was there any other questions before we go? Let's see if I can start the simulator. I keep getting things popping up. Were those chat questions or what?
They wanted to know, we wanted to confirm number 13, the initial temperature.
Okay.
I had a negative 8%, Fahrenheit, but someone said it was 56 or something.
No, okay. Okay. You had to wait until I hit the start button to see what initial temperature was. I know the question's out of order. When I did it before, it dropped to the original. Now it waits until I press this button. So wait until I press play and then look at that temperature. Okay? All right. Ready to go? I'm not sure mine's going to play now because it's not acting well. Okay? Ready to go? Any other questions before we start on Ice Age? Okay. Going to click on Ice Age. Here we go. Initial temperature -9, and it's dropping. You get a few photons coming down from the sun, sunlight photons coming down, a few, And now a few infrareds are coming up, and now the temperature has stopped dropping and it's going up now, but pretty slowly. Those the infrared photons are not nearly as vigorous as they were before. And our temperature seems to have stabilized right around 14 or 15 degrees Fahrenheit. Oh, it went to 17, 18.
So the temperature went up?
Well, yeah, it's going up, but only to around 19 or 20 now. 22. So you see it went up much, much, much more slowly than it did last time, and seems to be hovering around 21 and 22. Maybe now it's going up to 24, but it's below freezing because this is degrees Celsius, Fahrenheit.
Okay, so number 22, the temperature increased. Number 23, what are the first photons?
Were sunlight photons.
And after a time, which photons are greater, the infrared?
Yeah, but just barely. Not nearly as many as there were before, because you have fewer greenhouse gases.
Okay, sir, there seemed to be we're not all in agreement on the initial temperature for 13.
Okay, 13 was which? 1750?
Yes, sir.
Okay. Do we have everything for the Ice Age now?
Yes, sir.
No. What's the initial temperature for the ice age?
Okay, we'll go back and do it. Okay. Do we have everything? Have we answered all the questions for Ice Age besides initial temperature?
Yes, sir, that was all.
Okay. So let's reset everything. Let's stop it. Okay. And we'll reset everything. Reset all, yes. Now, your questions are for 1750 and Ice Age. Is that right?
Yes, sir.
Okay, I'm going to 1750. And just notice what, okay, let's go to today. Go back to today. Notice you have paved roads, big buildings, schools, or whatever that is, lots of houses, satellites, that's today. Now, don't pay any attention to this. That's not yet, okay? There were our greenhouse gases and stuff, but you got all that, right? So let's do 1750, okay? Notice the big buildings went away, the schools went away, or whatever the low building was. Most of the houses went away, the paved road went away. Now you got a farmhouse and, if anything, a dirt road, okay? Now, don't use this as your initial temperature. Initial temperature is when I hit start, okay? I haven't hit start yet. It's still waiting. So you got everything else you need off of here. Greenhouse gas concentration, 70% relative humidity, 280 parts per million carbon dioxide, 0.730 parts per million methane, and nitrogen oxide, 0.270 parts per million. Okay, ready to start. Now when I hit start, that's the initial temperature. Okay, so are you watching? Okay, I'm going to hit play. It goes down to -8 and starts dropping, and drops down till and you start seeing the sunlight photons coming from the sky. The temperature is still dropping. Okay, sunlight photons still coming from the sky, still dropping. Oh, and now you get a few infrared photons coming up from the ground, and the temperature starts going up. Okay, and the more infrared you get, the faster they go up, and they keep going up. Okay, and after a while they outnumber the sunlight photons, so your temperature keeps rising much more rapidly than it rose in the Ice Age. So any more questions on this? Do we need to wait till we get to equilibrium temperature? Or you got that? And
I think we're good.
okay, and y'all can play with this as much as you want to. Okay, we need to stop this. Reset. Is that right? And go to Ice Age. Reset all settings, yes. Except it doesn't change the temperature. I don't know why. And now we'll go to Ice Age. Okay, when we go to Ice Age, we lost the farmhouse, we lost the dirt road, we lost everything green that was in the field. Everything is brown or white, you know, no noticeable vegetation. Okay, it's bleak. Okay, now we've gone to blue on the greenhouse gas concentration. Relative humidity, we do not know. We don't have any indicator for that. Carbon dioxide, we know, was around 180 parts per million. Methane dropped to 0.380 parts per million. And nitrogen oxide dropped to 0.215 parts per million. Okay? Don't register the initial temperature until I hit the start button. And when you're ready for that, let me know. And if you need me to repeat any of that, I'll be glad to repeat it. Y'all can go and play with this yourself, you know. Ready to go? All right. Now, when I hit start, that's when we look for initial temperature. So I'm hitting play. Initial temperature -8, -9, and it starts dropping slowly. We start seeing a few photons from the sun come down, just like we saw before. Sunlight photons coming in. Temperature still seems to be dropping, and photons coming in. Gets down to about, and there we see our first of the red infrared photons going up. They don't go very far, they just go a little ways, but our temperature starts rising now to -6, -5, on like that, and it keeps rising. Now it's got above negative Fahrenheit, but we're still not above freezing. And as the infrared photons increase, so does our temperature. But it's a pretty slow process. So you let me know when you want me to stop, and we'll call the temperature then. After a while, I guess infrared outnumber the sunlight, but it's really close. Before it was heavily infrared. Not nearly as many infrared, and they're not nearly as active. Okay? Let me know when you want me to stop it.
You can stop.
Okay. So it got up to about 28 Fahrenheit. So it's below freezing. I think if we left it a little longer, it might warm up just a little bit, but that's basically about where we stopped the others too. They probably would have gotten a little hotter too. Are there more questions? I see things are popping up. Ooh.
Equilibrium temperature was 22, so I know you can mark that one wrong. Because you waited this time it went up to 28, but initially we stopped at 22 Fahrenheit.
That's fine. Yeah. That's perfectly fine. It's just, it's all sort of relative. Just depends on how long you're waiting. But the point is, it got up higher, modern, almost as high in 1750, but definitely not as high in the Ice Age. But the reason were fewer greenhouse gases. There was nothing producing methane, nothing much producing carbon dioxide. You know, it was pretty bleak. All right. Any other questions on the lab? I'll be glad to answer them. We'll redo anything you want to redo. Anybody? How are y'all? Okay? Any questions?
No, sir.
All right. You want to keep it up here a little bit longer? Anybody? Okay. Oh, yeah, I will. I've got to shut this stuff down and do a few other things, but yeah, then I'll be sending the test.
Okay, so let's go over this. This was not our last lab. We have one more lab.
One more lab, yes.
This week we got one more test.
One more chapter test, and then we have the final exam. Okay, so there'll be 9 labs, 9 chapter tests, 1 final exam, 1 research paper. That's pretty much it. I will drop your lowest lab score, and that means I'll average the other 8, and that gives you a number somewhere between 0 and 25, hopefully closer to 25. Then I'll average all your test scores and your research paper. I'll drop your lowest chapter test score. Won't drop the research paper, won't drop the final exam. You don't want me to drop the final exam. That's going to be the easiest test you have. So I won't drop the research paper or the final, but of those 9 chapter tests, I'll drop your lowest chapter test score if it helps your overall average, which should, but if you don't turn in a research paper and that's a 0, you need every score you can get. So I will drop the lowest chapter test score if it helps your average, and then I'll average those, your research paper, your 8 top chapter test scores with the final exam. That'll be a total of 10 test scores. The research paper counts as a test score, and average those together. Take 75% of that number, add it to the 25% or so that you get from your lab. That gives you your final average. And then if it's in the 90s, it's an A, at 80s, it's a B, the 70s, it's a C, and hopefully nobody will be any below that. All right. Any other questions, issues, concerns, problems? Okay. Okay, this recording, like I said, especially as slow as things have been today, it may not upload tonight. It may still be uploading when I go to bed at 10 or so. But if it does, I'll upload it tonight. If not, it'll be tomorrow morning. I've got 2 hours in the morning. I'll check it again then. But most of the time they do finish before the end of the day. But I did have one day a couple weeks ago, sometime or another, where it hadn't uploaded by 10 o'clock at night. I said, oh my goodness. And then the next morning it had uploaded. Okay. All right. Want me to stop sharing?
Yeah.
Okay. So I'm going to stop the sharing. And then, unless you have any further questions, we'll be ending the meeting for everybody. I'm cheating you out of almost an hour of your tuition dollars. I feel really bad about it, but are you okay with it?
Mr. Fowler?
Yes.
So we should have actually 9 labs, correct?
Not yet. This is lab number 8 today. Then the one we'll do next week will be number 9.
Okay.
And then I'll drop your lowest lab score.
I have a question.
Okay.
Okay, and our last test will be the just overall test for the semester. Is that taken in class during the class period, or will we have time outside?
It'll be just like your other test. I'll put it out there. You do it. You turn it back in.
Okay, because I usually go to work on Thursday. I was getting nervous.
Okay. No, I'll actually give it to you sometime, probably Tuesday evening, Wednesday morning, something like that, whenever I can put it out there. Probably Tuesday evening, all right? And then I'll still be here on Thursday of next week in case anyone has any last questions or needs to see something, go back and see a lab, or something didn't come through, or you couldn't yeah, I'll be here just as normal. I'll be sitting here grading papers and that kind of stuff to get your things in. So I'll be here every day that we're supposed to be here. Now, starting the following week, after this term's over, then I'll be in a Physical Science 2 class, okay? And that will be, I won't be available then, as available. Some of you will be in that class, and that'll be great. You can still ask me questions then. And y'all can always email me and stuff, but I'll be here during class times. Unless we all end early like we have today, then we'll be taking off. Did that answer your question?
Yes, it did.
All righty, good deal. Any others before we shut down the meeting? We've been losing people pretty quickly here, so I take it y'all are leaving, but any questions? Okay, if not, then we'll see you all on Thursday. Okay? All right, bye-bye.